Your adventure into the world of computer vision and the field of deep learning starts here. If you've ever wondered how to use deep learning to classify images and teach machines to see the world, but don't know where to start, then this course is for you. This course will set you up to go deeper into deep learning. You'll learn about the history of computer vision, convolutional neural networks, how those networks are trained, and how to train those networks using SuperGradients. Hi, I'm Harpreet Sahota, and for the past 10 years, I've worked as an actuary, biostatistician, and a lead data scientist. This computer vision essential training course is a roadmap I wish I had when I first started. It's a top-down, carefully crafted pathway that guided me from fear to mastery. You ready? Let's go. Computer vision essential training is more than just a course. It's the first step in your journey into deep learning. Whether you're an experienced data scientist, a seasoned machine practitioner, or simply curious about deep learning, this course will provide you with the fundamental knowledge you need to go deeper into deep learning. Your adventure into the world of computer vision and deep learning starts here. Here are a few important things you need to know before we begin. Here's what you need to know to start. If you're familiar with Python and have dabbled in building classical machine learning models like Random Forest or XGBoost, then you're on the right path. This class is for you. If you've got experience with Python training models in scikit-learn and are comfortable working in a Google Colab environment, then you're going to have a great time with this course. Suppose you're looking to brush up on deep learning frameworks. In that case, I recommend the course PyTorch Zero to Mastery as a perfect primer for deep learning and using PyTorch. But in this course, here's what you're going to learn. First is the foundations and history. You're going to dive into the fundamental concepts of computer vision, explore its early history, and uncover how the deep learning revolution took computer vision and the world by storm. You're going to learn about deep learning, specifically convolutional neural networks. You'll get hands-on with deep neural networks for image classification. You'll dissect the anatomy of deep learning architectures and master convolutional neural networks. You're also going to gain a unique perspective on the history and evolution of computer vision for image classification. You'll walk away understanding how a deep learning model works and explore the different components that make it tick. Throughout this course, you'll gain an intuition for deep learning. You'll see how to use PyTorch for image classification, and you'll learn how you can leverage SuperGradients, an open source training library, to train almost any image classification model, all within the comfortable environment of Google Colab. To follow along with this course, you want to download the exercise files from the related to this course section below. I look forward to seeing you excel in your career in deep learning, and thanks for taking this course as your first foray into deep learning. I want to start with some motivation for this course. David Marr raised a simple yet hard to answer question in his 1982 book, Vision. What does it mean to see? Pause for a moment and reflect on this quote. Marr noted, vision is more than knowing what is where by looking. It's discovering from images what is present in the world and where it is. We humans take our vision for granted. Something so easy and natural for us to do should be the same for machines. But our visual system is incredibly complex and involves multiple layers of processing and interpretation that have evolved over millions of years. A unique feature of our vision is the ability for our brains to quickly learn and adapt to new visual stimuli. You and I can learn new visual concepts and object recognition very efficiently, even with limited examples. Our vision generalizes visual concepts across different objects, colors, shapes, and positions, even when occluded or when noise is present. Replicating this level of complexity and adaptability in machines was a significant challenge in computer vision research. Images and videos contain intricate and dynamic patterns, requiring sophisticated algorithms to recognize and interpret. There often needs to be more clarity and certainty present in visual data, making it difficult for machines to accurately identify objects and events. Visual data varies significantly between natural scenes, medical images, and robot vision domains. Developing algorithms that match or surpass human-level performance has been one of the most challenging tasks in artificial intelligence. but it is a first step towards creating intelligent machines that can learn and adapt quickly to new visual stimuli, resembling more of a human-like learning experience. Before diving into modern image classification techniques, it's important to appreciate the milestones that advanced the field of computer vision. These ideas paved the way for developing more advanced techniques, including deep learning-based approaches that have significantly improved computer vision applications. The roots of computer vision go back as early as 1957, when computer image processing work began at the American National Institute for Standards and Technology. A group of engineers led by Russell Kirsch accomplished a remarkable feat by creating the very first digital scan of an image. This work paved the way for greater advancements in computer vision and revolutionized how humans interact with digital media. In 1966, Larry Roberts created the block world system, which could identify and track moving objects in a sequence of video frames. The block world system used edge detection and cross-correlation techniques to track objects in an image. In the late 1960s and early 1970s, work by David Marr and others led to the development of early computer vision research, including visual processing and object recognition theories. These theories emphasize the importance of using multiple levels of image processing to extract features and recognize objects. In 1979, a multi-layered neural network called the neocognitron was proposed by Kunihiko Fukushima that was used for Japanese handwritten character recognition and other pattern recognition tasks. Fukushima's work, as I'll discuss later, greatly influenced modern convolutional neural networks. In the 1980s, research in computer vision focused on developing methods for image segmentation, edge detection, and feature extraction. Techniques such as the canny edge detector, the random sample consensus algorithm, and the Hogue transform were developed during this time. The 1990s saw the rise of feature descriptors, such as the scale invariant feature transform, also known as SIFT, by David Lowe. These were the primary techniques used to solve various computer vision problems, ranging from image classification to object detection and facial recognition. Often, these feature descriptors were combined with traditional machine learning classification algorithms, such as support vector machines and k-nearest neighbors, to solve computer vision problems. In 1998, a paper by Jan LeCun called Gradient-Based Learning Applied to Document Recognition introduced the first convolutional neural network. LeCun's work was greatly influenced by Fukushima's neocognitron. In 2001, Paul Viola and Michael Jones proposed a real-time face detection algorithm that used HAR-like features and boosted cascades. This was one of the first successful applications of machine learning in computer vision. In 2005, Navneet Dalal and Bill Triggs introduced the histogram of oriented gradients, or HOG, which is a feature descriptor for object detection. This method is still used today in different forms and object detection models. 2005 marked another milestone in computer vision history. This was the year that the Pascal VOC dataset was published. This dataset contained 4 categories: bicycles, cars, motorcycles, and people. For the first time, the computer vision community had a standardized dataset to use for object classification and object recognition tasks. In 2006, the Speeded Up Robust Features, or SURF, method was published by Robert Bay and others. In 2009, ImageNet was presented for the first time at the Computer Vision and Pattern Recognition Conference. And in 2010, the first ever ImageNet Large-Scale Visual Recognition Challenge was organized. In 2012, Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton showed that deep convolutional neural networks could outperform traditional computer vision techniques on the ImageNet dataset, marking the beginning of the deep learning revolution in computer vision. These early milestones represent important steps in the development of computer vision, laying the foundation for the research that would later lead to more sophisticated techniques such as deep learning. Let's now talk about some of the limitations of traditional computer vision techniques. Before deep learning, computer vision focused on using feature extraction to recognize patterns in images. This involved manually engineering features, and by that I mean writing code that would detect the corners, diagonal lines, oriented edges, and various shapes of an object, and then combining those in a nearly infinite number of ways to express an object. A problem with manual features, again, is just the sheer number of ways that the features can be combined to describe an object. For example, creating a model that can recognize a cat using just 10 features representing parts of the face, body, and ear would require nearly infinite combinatorial possibilities. These features were then used in classifiers like template matching or in statistical models such as Gaussian, SVMs, or random forest to then recognize and classify an image. These methods did have their limitations. They relied on domain experts who understood the data sets and the specific feature extraction techniques that would work on those specific data sets. As you can imagine, this required a ton of manual effort. And these techniques had an inability to handle complex visual data, like images with occlusions, or different lighting variations, or the different non-rigid deformations that could occur. As powerful as techniques like SIFT and HOG were at addressing some of these challenges, they still fell short when it came time to handle complex scenes. But these early developments in computer vision, they lay the foundation for more advanced techniques such as deep learning. By building on these methods and incorporating neural networks, object detection and classification systems using deep learning could use their ability to learn directly from raw data without relying on manual feature extraction. The drive for further development in deep learning stems from the necessity for more advanced techniques. Up until 2009, one of the biggest challenges faced by computer vision researchers was the lack of diverse data sets. Before then, researchers used smaller domain-specific data sets for training and testing computer vision systems. This made it difficult to develop general-purpose systems. There were a few curated datasets that researchers were working on, like CFAR 10 and CFAR 100, as well as Caltech 101, Caltech 256, and of course, Pascal VOC. But these datasets lacked diversity in terms of the types of images and object categories that were present, as well as the number of images that were present. This made it challenging to develop a general-purpose computer vision system that could work across a variety of domains. As I've already mentioned, these existing datasets for image classification were small and limited in scope. To truly advance computer vision, a much larger dataset was needed. This all changed with the introduction of the ImageNet dataset in 2009, created by Fei-Fei Li and her team at Princeton University. ImageNet changed the trajectory of computer vision research. It helped researchers tackle the problem of overfitting so they could build models that generalized well. Let's talk a bit about the importance of data for building image classification models and the lasting impact of ImageNet on computer vision. One of the fundamental principles in machine learning is the avoidance of overfitting, which is crucial for achieving generalization. These two concepts, overfitting and generalization, go hand in hand, and you need to think about them together. To achieve strong generalization, you need powerful models. But to build a powerful model that avoids overfitting and achieves good generalization, you need to have enough data to support the complexity of that model. Without sufficient data to constrain the model, it will likely fit the training data too closely and fail to generalize well to new unseen data points. And this line of thinking led a researcher named Fei Li to the realization that there was too much focus on models and too little on data. Recalling a 1983 paper by Irving Biederman that suggested humans could identify something like 30,000 object categories by age 6, Fei looked at the current state of computer vision, where researchers were tackling datasets with only 20 objects. Li realized the chasm between research and reality. She hypothesized that moving computer vision forward required larger, curated, labeled datasets. I was listening to a podcast featuring Fei Li on the Robot Brains podcast. And on that podcast, Fei Li discussed a chance encounter at Princeton University with a linguist named Christian Fellbaum. This was back in 2007. Li came to learn about a project Fellbaum's team was working on called WordNet. WordNet is a database of English words designed to capture lexical and semantic relationships between words. On that same episode of the Robot Brains podcast, Li describes the moment she learned about WordNet and described it as a game changer. Realizing that a vast collection of images structured according to WordNet's ontology could be instrumental in achieving object recognition, she set out to curate a massive image dataset that she believed would revolutionize the fields of computer vision and machine learning. In spite of a lukewarm reception and much criticism at the 2009 Computer Vision and Pattern Recognition Conference in Miami, Li decided she would launch the ImageNet Large-Scale Visual Recognition Challenge in 2010. In this challenge, competitors classified images of objects and scenes across 1,000 categories. This competition encouraged researchers to develop increasingly accurate object detection and classification models. The competition served as a benchmark for progress in the field of computer vision and spurred innovation and collaboration among researchers. It's difficult to say for certain, but the deep learning revolution would likely have been delayed or slowed down significantly if it were not for ImageNet. Other datasets, such as CFAR and MNIST, were available before ImageNet, but they were much smaller and far less diverse. ImageNet provided a massive dataset of labeled images, which allowed researchers to train deep neural networks to recognize and classify objects with unprecedented accuracy. ImageNet has enabled the development of transfer learning, which we'll learn about in a later section. Transfer learning has been a breakthrough in deep learning research. By training a deep neural network on a dataset as large and complex as ImageNet, researchers can leverage the learned features from that network to other computer vision tasks, even with smaller or different datasets. In practice, this means that researchers can train deep learning models for many image classification tasks with smaller amounts of training data, making the development of computer system and artificial intelligence systems more accessible. Today, the ImageNet dataset is one of the most famous and widely used image classification datasets in deep learning. In its current form, it contains over 14 million labeled images, organized into 21,000 categories. To this day, ImageNet is used to pre-train new models for computer vision applications. ImageNet revived the field of deep learning, and the community is forever indebted to Fei Li and her team for curating this landmark dataset. In 2012, a revolution took place that has shaken the tech world and has undoubtedly changed the way humans interact with technology forever. That revolution is the deep learning revolution. Up until 2012, computer vision researchers were making slow yet steady progress in object recognition in images. Models were improving on benchmark datasets, but only by a small percentage point every year. The best performing model in ImageNet at the time had achieved a top 5 error rate of 26.2%. Progress was limited because techniques at that time, as we've discussed previously, required domain experts to identify and engineer features required to differentiate between object categories. But the application of neural networks for vision tasks isn't something that came out of nowhere. Methods for training convolutional neural networks end-to-end using backpropagation had existed as early as 1989. For example, we've already discussed neural networks by LeCun and Fukushima. These networks were successfully applied for character recognition problems. However, these methods have fallen out of favor and were underestimated. Machine learning researchers didn't think neural networks could perform well on difficult tasks such as image recognition, and instead favored more traditional machine learning approaches like decision trees, support vector machines, and boosting algorithms. This view was largely due to the limitations of neural network architectures used at the time and the difficulty in training deep neural networks. All that changed on September 30th, 2012. This was the day Jeffrey Hinton and two students of his, Alex Krzyzewski and Ilya Sutskever, submitted their results to the ImageNet Large-Scale Visual Recognition Challenge. Their model, which has come to be known as AlexNet, obliterated the competition. AlexNet became the first submission to the competition to achieve an error rate below 25%. It achieved a top 5 error rate of 15.3%. which was 9.8% lower than the runner-up. To put this improvement in perspective, the top 5 error rate for the winning entry in 2011 was 25.8%, meaning that AlexNet cut the error rate by more than half compared to the previous year's winner. The breakthrough success of AlexNet in the ImageNet Large-Scale Visual Recognition Challenge was a major turning point for computer vision and artificial intelligence. It helped spark renewed interest and investment in deep learning research. AlexNet also demonstrated the potential of deep learning to achieve state-of-the-art performance on challenging visual recognition tasks. This has since led to a resurgence in interest in neural networks and the emergence of the deep learning revolution in artificial intelligence. But as we've discussed before, the ideas behind deep learning and AlexNet existed well before 2012. AlexNet is a direct descendant of a method that was over 30 years old at the time, the convolutional neural network. Since 2012, every winner of the ImageNet Large-Scale Visual Recognition Challenge has been a convolutional neural network, with more recent entrants achieving top 5 errors of less than 2.5%. But what are CNNs? They're deep neural networks that are designed to process data with a grid-like structure, such as images and videos. They have been proven to be effective at image classification, object detection, and other computer vision tasks. And they have been used to achieve state-of-the-art results on benchmark datasets such as ImageNet. Let's now turn our attention to the essential building blocks of a convolutional neural network. Convolutional neural networks are deep neural networks that excel in image recognition and classification tasks. They're designed to learn spatial hierarchies of features from raw data automatically. The components of a CNN comprise the input layer, convolutional layers, activation functions, pooling layers, fully connected layers, and an output layer. The input layer is where raw data, like an image, enter the network. Images are represented as arrays of pixel values. In a convolutional layer, the layer applies filters, which are a collection of kernels, to the input image. The filters slide across the input, performing element-wise multiplication and summing up the results. This process detects local patterns in the input data, such as edges and textures. As I was mentioning, the convolution operation is sliding a filter over the image, and it's examining small chunks of pixels at a time. At each step, as we're striding over the input, we're multiplying the values of the filter with the corresponding image pixels in that chunk. The resulting values get added up to produce a single value in the new output volume. You keep sliding that filter and repeat the process for the different regions in the image. So as you're sliding over, we call that a stride. This is helping the network identify patterns and detect features like edges, textures, or shapes. The output volume ends up representing a transformed version of the original. Think of it like the filter acting as a spotlight that shines on different parts of the image, highlighting interesting details. It's through this process of convolving the filter across the image that the network learns to recognize objects and make sense of visual information. after the convolution, an activation function, such as the rectified linear unit, or ReLU for short, is applied. Activation functions introduce a non-linearity into the model, enabling it to learn more complex patterns. Convolutional neural networks also have pooling layers, and pooling layers downsample the previous layer's output and reduces its spatial dimensions. Max pooling is a common technique for keeping the maximum value within a local region. We use pooling because it helps increase computational efficiency and reduce overfitting. Max pooling, what it does is it takes a chunk of values from the feature map and picks only the largest value within that chunk and discards all the other values. This helps identify the most prominent feature or highest activation in that area. Max pooling is great at capturing the presence of a particular feature like edges or corners, regardless of their exact position in the input. You can also use average pooling. Now, average pooling, it takes a chunk of values from a feature map and calculates the average value within that chunk. This helps capture the overall intensity or magnitude of features present in that neighborhood. So it's good for global information, and it's useful for detecting general patterns and structures in an image. So to recap, max pooling emphasizes the most prominent features, while average pooling will give a more holistic view of that region in the image. And these are commonly used to downsample feature maps, and it helps reduce the spatial dimensions and enhance computational efficiency. Next is the flattening layer. So in a convolutional neural network, when we talk about flattening, what we're doing is we're taking a multidimensional input like a feature map or some volume, and we're converting this into a one-dimensional vector. So flattening is necessary because subsequent layers in the neural network often will require the input to be in a certain format, such as a one-dimensional vector. And so by flattening the input, we can easily pass it through these layers, and this helps actually preserve spatial relationships that are present in the original data. This is then followed by fully connected layers. So in a fully connected layer, each neuron is connected to every neuron in the previous layer. So each connection has its own weights and allows the layer to learn complex relationships between the input and output. So the neurons in these layers take that flattened input and they perform multiplication with their weights. This is followed usually by some activation function that's going to add more nonlinearity to the computation. And so fully connected layers are responsible for extracting high-level features and making predictions when it gets to the output layer based on those learned representations. So they play a role in tasks like classification, whether it's binary or multi-class classification. So that's what flattening does. It's preparing the input to be compatible with subsequent layers, while the fully connected layers, they kind of handle the heavy lifting of learning complex relationships and making predictions based on the extracted features. To put it all together, here's a great video by Ratish Mishra, who is showing how a convolutional neural network looks when it's animated. So we have an input image that goes through some convolutional layers into a max pooling layer, and then finally through a series of flattening and fully connected layers to arrive at a output. So it's a great video to check out if you want to get further intuition about how convolutional neural networks make predictions. Let's now explore the reasons behind convolutional neural networks' superior performance, shedding light on their unique design, efficiency, and ability to capture spatial hierarchies. Vanilla neural networks, or fully connected networks, treat input data as a flat vector of features, neglecting spatial relationships between the features. In contrast, CNNs are specifically designed to exploit the spatial structure of input data, such as an image. CNNs apply filters to capture local patterns like edges, corners, and textures through their convolutional layers. This ability to detect and learn spatial hierarchies of features is critical for image classification tasks, giving CNNs an edge over their vanilla counterparts. Another advantage of CNNs is their parameter efficiency. In a fully connected network, each neuron in one layer connects to every neuron in the next layer, leading to an explosion in the number of parameters needed to represent your data. This increases the computational cost and the risk of overfitting, as the model may learn noise from the training data. CNNs, on the other hand, use shared weights in their convolutional layers, which reduces the number of parameters needed to represent your data. This weight sharing allows CNNs to learn spatial features more efficiently with less risk of overfitting. In image classification tasks, the position of an object within an image often varies. Vanilla neural networks lack translation invariance, meaning they struggle to recognize an object if it appears in a different position or orientation than what the network was trained on. This limitation can severely hinder the performance in image classification tasks. CNNs address this issue of translational invariance through convolution and pooling layers, which enable the network to recognize spatial features regardless of their location in the image. This translation invariance is essential for robust image classification. It allows a model to generalize and recognize objects in various positions and orientations. To sum it all up, CNNs are specialized in capturing and comprehending spatial information, especially in recognizing intricate visual patterns. Spatial processing allows for the analysis of complex visual data, making CNNs highly efficient in image classification and object recognition. Additionally, CNNs learn spatial hierarchies to tackle complex visual patterns better. Convolutional layers form the backbone of convolutional neural networks. They are specifically designed to capture spatial features in input data like images. Let's break down the essential concepts and walk away with a detailed understanding of convolutional layers. Filters are a collection of small matrices with trainable weights that the network learns during training. Each filter is responsible for detecting a specific feature in the input data. The depth of the feature should match the depth of the input data, meaning a 3-channel red, green, blue image requires a filter with 3 channels. Each channel in a filter is referred to as a kernel. As the network trains, the filter learns to detect more complex and higher-level features, forming a hierarchy of learned features. Combining multiple filters allows the network to capture various features simultaneously. Note that 3x3 convolutions are widely used in CNNs due to their efficiency and effectiveness in capturing local features. 3x3 convolutions provide a good balance between a small receptive field and computational complexity. Filters in convolutional neural networks detect specific features in input data using trainable weights. The depth of a filter matches the input data's depth, and filters learn more complex features during training. Combining multiple filters helps capture various features at once. The receptive field refers to the input region contributing to an output feature map. 3x3 convolutions strike a balance between a small receptive field and computational complexity. Stacking 2 3x3 layers can capture the same information as a single 5x5 layer with fewer parameters and computations. The convolution operation in a CNN involves sliding a filter or kernel, which is just a small matrix, over the input data, which is typically an image. The filter is applied to local regions of the input in a sliding window manner. At each position, an element-wise multiplication between the filter and the local region of the input is performed, and the results are summed up to produce a single value in the output feature map. This operation captures local patterns in the input, such as edges, corners, and textures. When we talk about applying a 3D convolution over a RGB image, what we mean is we're using a filter that has dimensions 3x3x3. So that's width, height, and depth to perform the convolution operation. So consider a RGB image, a red, green, blue image. Each pixel in the image has 3 color channels. That's red, green, and blue. So the image itself can be visualized as a 3D volume, where the width and height represent the spatial dimensions and the depth represents the 3 color channels. So now let's talk about this 3x3x3 convolution, right? So the filter or kernel has the same depth as the input image's color channels. So this means that each layer of the convolutional filter corresponds to one color channel. During the convolution operation, the filter strides over the RGB image. It examines a small 3 by 3 by 3 chunk of pixels at a time. And at each step, the filter does element-wise multiplication with its values in the corresponding pixels. So the resulting values are summed up, and it creates a single value in the output volume. So this process is repeated for different regions of the image. So it's capturing local patterns and features. So as the filter strides over the image, it performs computations that help the network understand relationships between the neighboring pixels, colors, and patterns across the 3 dimensions. So to kind of drive this point home, right? If we have a 3D filter, 3 by 3 by 3 filter, we need to multiply each of the 27 numbers in the filter with the corresponding numbers from the input volume's red, green, and blue channels. So we take the first 9 numbers from the red channel, followed by the 9 beneath it in the green, and the 9 beneath it in the blue. So we multiply these numbers with the corresponding 27 numbers that are covered by this yellow cube on the far left. And once you do this, you add up all the numbers to get the first output. To compute the next output, stride the cube over by 1 and repeat the process. And so we do this for every position of the cube to get all the outputs. And the end result of this operation is one feature map. And in this case, it's a 4 by 4 feature map. And that is how you do a convolution operation over a volume. The stride refers to the number of pixels by which the filter moves or slides across the input data. A stride of 1 means the filter slides 1 pixel at a time, resulting in a densely computed output feature map. A larger stride, like 2 or more, skips pixels, leading to a sparser output feature map and reduced spatial dimensions. A larger stride can increase computational efficiency, but may also result in a loss of spatial information. When we apply a convolution operation, the size of the output volume can vary depending on factors like the size of the input volume, the size of the filter, and the stride. So padding is a technique used to control the spatial dimensions of the output volume. What we see on the screen now is no padding. And no padding means that we don't add any extra border or pixels around the input volume before applying the convolution. So in this case, the filter is going to slide or stride through the image if the entire filter fits within the input volume. And so the result is a output volume that will have smaller spatial dimensions compared to the input volume. On the other hand, there's something called padding same or same padding. So this is a technique where we add an extra border or pixels around the input volume before applying the convolution. So this padding is added symmetrically to all sides of the input volume so that the spatial dimensions of the output volume remain the same as the input volume. So padding helps maintain the spatial information and resolution from the input throughout the convolutional layers. So this is useful for preserving fine-grained, detailed, and accurate spatial relationships in the volume. By adding this extra padding, the filter can now slide through the entire input volume, even reaching pixels at the edges. So this prevents information loss due to the reduction in spatial dimensions during the convolution operation. So to sum it all up, no padding leads to smaller output volumes compared to the input, while same padding will preserve the spatial dimensions of the input volume in the output volume. The choice between these two depends on factors like the desired output resolution and the importance of preserving fine details and spatial relationships in your network. There are several types of convolutions used in convolutional neural networks, each with unique characteristics that make them suitable for specific tasks or scenarios. Let's talk about some of the most commonly used types of convolutions. First is a standard convolution, often called a 2D convolution, which is the most widely used type of convolution operation. To understand a 2D convolution, think of sliding a 3D filter through an input layer. Both the input layer and filter have the same channel number. The filter moves in 2 directions, along the height and the width of an image, even though it has 3 dimensions. This is called a 2D convolution and creates a 1-layer matrix as an output. This convolution type captures spatial features in images, like edges, corners, and textures. Depthwise convolutions are computationally efficient variants of the standard convolution. In a depthwise convolution, each input channel is convolved with its corresponding filter, producing one output feature map per channel. The output feature maps are then stacked together to form the final output. This approach reduces the number of computations and parameters, making it faster and more memory efficient than standard convolutions, while still effectively capturing spatial information. As you recall, in the regular convolutions, we use a single filter to extract information from all channels of an input simultaneously. However, the depthwise convolution is operating on each channel independently, as you can see here. So imagine we have an input volume with multiple channels. For example, a red, green, and blue image. Depthwise convolution, we're going to apply a separate filter, as you can see here. A separate filter is applied to each channel. So if we have 3 channels, we have 3 filters, each with size of, let's say, 3 by 3, which we have here. Now for each channel, the corresponding filter, as you see here, is going to slide over the input, examining a small 3 by 3 region at a time, and is performing the element-wise multiplications between the filter and the input region for each channel independently. These multiplications generate new channels with filtered information from each channel. Now, after processing all the channels with their respective filters, we combine the results to obtain the output volume. This combination can be as simple as just concatenating the filtered channels together. So the advantage of using a depthwise convolution is the reduction in computational complexity and the number of learnable parameters. By applying separate filters to each channel, we're avoiding intermixing information across channels, and then this leads to more parameter-efficient and lightweight models. One-by-one convolutions, also known as pointwise convolutions, are used to change the depth of the feature maps without affecting their spatial dimensions. They help in reducing the number of channels or combining information from different channels. These convolutions are computationally efficient and are often used in combination with depthwise convolutions. For example, the depthwise separable convolutions, or in more complex architectures like the inception network to reduce computational complexity. So let's illustrate a little bit further what a pointwise convolution is doing. So suppose we have an input volume with n channels. In a pointwise convolution, we apply n separate one-by-one filters to each pixel location across all channels of the input volume. At each pixel location, the one-by-one filter performs element-wise multiplication between the filter weights and the corresponding channel values. These multiplications generate new values for each channel. The output at each pixel location becomes a linear combination of the input channels, and it produces a new set of channels, and the number of output channels can be determined by the design choice of the network. A pointwise convolution plays several important roles in a CNN. It plays the role of dimensionality reduction. By adjusting the number of output feature channels, pointwise convolutions can change the depth of a volume. Not only can it reduce the number of feature maps, but we can use pointwise convolutions to increase the number of feature maps. They also perform a role of feature mixing. So they allow for the mixing and interaction of different information between channels. So they're commonly used in conjunction with depthwise convolutions to create the depthwise separable convolutions, which further reduce computational complexity while maintaining good representation learning capabilities. And we'll learn about the depthwise separable convolution in the next slide. Depthwise separable convolutions, as was previously mentioned, combines depthwise and pointwise convolutions. First, a depthwise convolution is applied to capture spatial information. Then, the pointwise convolution combines the spatial features and increases the output feature map's depth. This technique further reduces the computational complexity compared to a standard convolution while maintaining similar performance, making it a popular choice for lightweight models such as MobileNet. Let's drive the concept of the depthwise separable convolution home with another awesome graphic from animated AI. So in the depthwise convolution step, we're first applying filters to each channel independently. By doing this, we're focusing on capturing spatial relationships within each channel. This step helps identify and extract the most important features from each channel separately. Next, we have the pointwise convolution step. So we bring together all the filtered channels that were obtained from the depthwise convolution, and we use a one-by-one filter. And the one-by-one filter is the pointwise convolution, which is picking up cross-channel interactions. So the pointwise convolution is simply performing a linear combination, multiplying and adding things together. And it does this for the filtered channels. This is allowing the network to now mix and transform the features across the different channels. So the depthwise separable convolution, it's breaking down the convolution operation into two steps. One is capturing spatial relationships within the channel with the depthwise convolution, and then the other is capturing cross-channel interactions with the pointwise convolution step. So doing this is reducing the computational complexity and parameter requirements compared to the traditional convolutional layer. But at the same time, it's maintaining the ability to capture and transform the most important features. So just recapping, first step is the depthwise convolution. Each input channel is convolved separately with a dedicated filter. This results in a set of filtered feature maps. After the depthwise convolution, we're performing the pointwise convolution, which is a one-by-one convolution. So you use a one-by-one kernel to combine and transform the filtered feature maps obtained from the depthwise convolution. And this is, again, breaking down the traditional convolution into two separate steps, but it's reducing the computational complexity, it's improving parameter efficiency, and still maintaining good learning representation capacities. So by doing this, we're actually doing fewer multiply and addition operations, which again is going to save on computational complexity. Dilated convolutions, sometimes called atrus convolutions, introduce a dilation factor to the standard convolution operation. This factor determines the spacing between the filter's values, effectively expanding its receptive field without increasing its size or the number of parameters. Dilated convolutions are particularly useful in tasks that require capturing information at multiple scales or resolutions, such as image segmentation and object detection. So the dilated convolution, as we learned, is a variant of the traditional convolution, and it introduces a parameter called the dilation rate. So dilated convolutions, they offer a expanded receptive field, and this allows the network to capture larger patterns and context. In the regular convolution, if you recall, we slide a kernel over the input using a fixed stride, typically a stride of 1. So this process is considering the neighboring pixels within the receptive field, and it does that to compute some output for the feature map. But dilated convolutions, they modify this behavior by introducing a gap within the kernel. So suppose we had a 3x3 kernel with a dilation rate of 2. So rather than sliding the kernel across the input pixel by pixel, we're skipping pixels according to the dilation rate. So in this case, we move the kernel center by 2 pixels instead of 1. This is effectively increasing the spacing between the kernel's sample locations. So because the dilated convolution introduces gaps, it is increasing the receptive field without increasing the number of parameters or computational complexity of this convolution. So we're now able to see a wider receptive field. This helps the network capture larger patterns, more global context, and even long-range dependencies within the input volume. So as we mentioned, this is useful more so in the context of semantic segmentation. This is where you'll see it used the most. And again, this helps capture the long-range dependencies and context in an image. Transposed convolution is used to upsample or increase the spatial dimensions of input data. This type of convolution is common in tasks like image segmentation and generative models, where the goal is to produce an output with higher resolution than the input. Transposed convolutions work by applying a learnable filter to the input data in such a way that it expands rather than reduces the spatial dimensions. Implementing a transposed convolutional layer can be better explained as a 4-step process. First, you calculate new parameters, z and p prime. Then you insert z zeros between the rows and columns of the input. Then you pad that modified input with p prime zeros, and you perform the standard convolution on the padded image with the stride of length 1. So as you recall, in the regular convolution, we're sliding a small filter or a collection of kernels over an input image, and then we're applying that to each neighborhood of the pixels. So this operation is extracting features by performing that dot product that we had discussed between the filter and the input values at every spatial location. But transpose convolution is like the inverse of a regular convolution. So it's used to upscale or expand a low resolution feature map into a higher resolution. So it's going from a coarse representation to a more detailed one. So imagine you have an image that's been downsampled, which means that it's been reduced in size so you can capture more salient information at a lower resolution. The transpose convolution is going to allow you to reconstruct the lower resolution image back to its original size. And it's doing this by filling in gaps and adding details that were lost during downsampling. So the transpose convolution is effectively spreading out information from each output location to multiple input locations. So we're able to create a more detailed picture by filling in some missing information. So now you've learned about the many different types of convolutions that exist. There's a bunch of other ones out there, but these are some of the most common ones. So let's recap them. The standard 2D convolution captures spatial features effectively. And this involves sliding a 2D filter over the input data to detect edges, corners, and textures. Then we talked about the depthwise convolution. This enhances efficiency by convolving each input channel separately. So this reduces computational complexity. Then we talked about pointwise convolutions, which manipulate depth without affecting spatial dimensions. This again improves efficiency by reducing the number of channels and combines information. Then we have the depthwise separable convolution that combines efficiency and lightweight design so that we can capture spatial information while at the same time reducing complexity. Then we also talked about dilated convolutions. And this is the convolution you use if you want to expand your receptive field without increasing size or parameter count, which you can then capture multi-scale information. Then we talked about the transpose convolution, which enables upsampling or increasing spatial dimensions for tasks like image segmentation and generative models. As was mentioned, there's several other types of convolutions that we didn't get into. For example, there's flattened, spatial, cross-spatial, groups, shuffled group convolutions. By leveraging these convolution layers effectively, you can design powerful CNNs for computer vision tasks. Now let's talk about pooling layers. Pooling layers are essential components of convolutional neural networks. They're used to reduce the spatial dimensions of feature maps while retaining important information. Pooling layers reduce feature map size, resulting in fewer parameters and computations needed for increased efficiency. Pooling in CNNs add spatial invariance, making the network less sensitive to small input variations. This, in turn, enhances the network's ability to generalize to new examples with slight variations compared to the training data. Hierarchical feature learning uses pooling and convolutional layers to teach the network various features. Deeper networks tend to have wider receptive fields and learn higher level features. This organization creates complex and abstract representations from input data, leading to better performance on computer vision tasks. Now let's talk about common types of pooling layers that you are going to encounter. Max pooling is the most commonly used pooling operation. In max pooling, a small window, either a 2x2 or 3x3 window, slides over the input feature map. The maximum value within that window is selected for the output. Max pooling retains the most prominent features while discarding less important information. If the input undergoes a small translation, the most prominent features will likely still be captured within the pooling window, and the output feature map will remain relatively unchanged. This robustness allows the network to focus on the essential characteristics of the input data, even when it's slightly altered. Average pooling is an operation that calculates the average value of the data within a specific window. Unlike max pooling, which focuses on the most important and prominent features, average pooling considers both prominent and less prominent features to provide a balanced representation of the local region. This results in a smoother representation of the feature map, which can be advantageous in situations where retaining the general information is more important than focusing on specific features. Depending on the task and input data, this operation can have varying properties and generalization capabilities within the network. Global average pooling is a technique used in CNN architectures to reduce the dimensions of a feature map down to a single value. It does this by calculating the average of all the values in a feature map. This technique is useful because it captures the global context of the input feature map and compresses high-dimensional information into a compact representation. Global average pooling considers both prominent and less prominent features, reflecting the general information in the feature map. It's commonly used before the final classification layer in CNN architectures, which replaces the need for fully connected layers and further reduces the number of parameters. Next is adaptive pooling. So adaptive pooling adjusts the pooling window size based on the input feature map's dimensions and desired output size. So this technique is useful if you want to vary input sizes and ensures for efficient pooling operations. Traditional pooling techniques might not be suitable for all feature maps. This leads to inefficient or unsuitable pooling. So adaptive pooling solves this by automatically determining the appropriate window size and stride for efficient and well-adapted pooling. To wrap it up, these pooling layers are prevalent in modern CNN architectures because they contribute to the network's ability to learn hierarchical features, reduce the number of parameters and computational complexity, and improve generalization by introducing a level of spatial invariance. Understanding these commonly used pooling layers and their rationale will help you design more efficient and effective CNN architectures for various computer vision tasks. Activation functions are critical in neural networks. They introduce nonlinearity into the network, enabling it to learn complex relationships and patterns in the input data. Without activation functions, neural networks would be limited to modeling linear relationships, which is going to be insufficient for solving real-world complex problems. Let's examine some common activation functions and their properties. First is ReLU. ReLU stands for Rectified Linear Unit. The formula for ReLU, as shown here on the graph, is f of x is equal to the max of 0 or x. So what does that mean? Any value less than 0 will get clipped to be 0, and we only keep all values that are greater than 0. So ReLU is a piecewise linear function, and it sets all negative input values to 0, and again retains positive input values. The ReLU activation is simple and computationally efficient. By keeping positive values unchanged and setting negative values to 0, ReLU allows the network to learn sparse representations, which will help reduce overfitting. ReLU also helps mitigate the vanishing gradient problem, as its gradients are either 0 or 1 for positive input values, enabling faster learning. However, ReLU units can suffer from dead neurons, where activations become stuck at 0. Next, we have the sigmoid function. So the sigmoid function maps input values to a range between 0 and 1, which could be useful for representing probabilities or generating binary outputs. And as you can see here on the graph, the formula is 1 over 1 plus e to the negative x. This function is smooth and differentiable, which makes it suitable for backpropagation. But the sigmoid can suffer from the vanishing gradient problem, where gradients become very small for large positive or negative input values, leading to slow learning. Next is the hyperbolic tangent activation function. So the hyperbolic tangent function is similar to the sigmoid function, but it maps input values to a range between -1 and +1, providing a more balanced output with zero-centered data. It's also smooth and differentiable. Like the sigmoid, the hyperbolic tangent can suffer from the vanishing gradient problem, but generally provides better performance due to its output range being centered around 0. Next, we have the GELU, or Gaussian error linear unit. So GELU is a small differentiable activation function that's inspired by the Gaussian error function. It behaves similarly to the ReLU function for large positive input values, but unlike ReLU, it's non-zero for negative input values. GELU has performed well in deep learning architectures, particularly in the context of transformer-based models. Next, we have the SILU, or sigmoid linear unit activation function, which is also known as the swish activation function. So the SILU is a smooth differentiable activation function that combines the properties of sigmoid and linear functions. SILU often outperforms ReLU as it could better capture complex patterns and relationships in the data. SILU introduces the concept of self-gating, which allows the network to learn adaptively and balance between linear and nonlinear behavior. And the final activation function that we'll talk about is the ReLU6. So the ReLU6 is a variant of the ReLU activation function that clips the output at an upper bound of 6. By limiting the maximum output value, ReLU6 introduces an additional nonlinearity, which can help improve the network's performance in specific scenarios. ReLU6 is particularly useful in scenarios where a bounded output range is desired, such as when using quantized weights and activations in low-precision neural networks. There are many other activation functions that we didn't cover. Each activation function offers unique characteristics that could benefit the learning capabilities of CNNs in different ways. When selecting an activation function, it's important to consider the specific problem and network architecture you're working with and the trade-offs between computational efficiency, robustness, and potential issues like vanishing or exploding gradients. Experimenting with different activation functions can help you find the most suitable one for your use case. In convolutional neural networks, fully connected layers help make predictions based on the features learned by the previous layers. Fully connected layers enable the network to map the high-level abstract representations of the input data, which were extracted by the previous layers, to the desired output, which in the case of image classification is the classification label. When it comes to generating the final output, the fully connected layers are critical for interpreting and combining the features learned by the earlier layers. In image classification, these help transform the high-dimensional feature maps into a probability distribution over the target classes. So again, in image classification tasks, the previous layers generate high-level abstract features of the image. These features are then taken up by the fully connected layers, which learn to combine and interpret them and map them to the desired output, which in our case is going to be class labels. The fully connected layers also learn to weigh the importance of different features and their relationship to the final prediction, which can often be complicated and nonlinear. Let's walk through what happens in the fully connected layers. So flattening prepares the feature maps for the fully connected layers. You're left with feature maps after the convolution and pooling layers processed your input data. These feature maps are typically multi-dimensional arrays. In order to feed these feature maps to the fully connected layers, you need to flatten them into a single one-dimension vector. This is done by concatenating the elements of the feature map along the depth dimension. So you end up with a single long vector. Each fully connected layer has a weight matrix W and a bias vector B. The weight matrix has a dimension n by m, where n is the number of neurons in the current layer and m is the length of the flattened vector. The bias vector has a dimension equal to the number of neurons in the current layer. These weights and biases are the learnable parameters of the fully connected layer. The input vector is multiplied by the weight matrix of the fully connected layer, and the bias vector is added to the result. This operation can be expressed as the formula W times input plus B. The output is a new vector that represents the weighted sum of the inputs from the previous layer. The weight matrix and bias vector determine how the input is transformed and combined to create the output. The output is a new vector that represents the weighted sum of the inputs from the previous layer. The weight matrix and the bias vector determine how the input is transformed and combined to create the output. After calculating the weighted sum of the inputs and adding the bias, an activation function is applied element-wise to the output vector. Remember that the activation function introduces nonlinearity into the network, which helps learn complex relationships between the input and output. A CNN's last fully connected layer is typically responsible for generating predictions. This layer has as many neurons as classes or categories in the task. The activation function used in the final layer often differs from those used in previous layers. The softmax activation function is commonly used for multi-class classification tasks, as it converts the output into a probability distribution over the classes. The neuron with the highest probability in the final output layer represents the network's prediction. In classification tasks, the index of this neuron corresponds to the predicted class label. Fully connected layers in convolutional neural networks serve as the final step in interpreting the features learned by the convolutional layers, which allows a network to generate predictions or other desired outputs based on the input data. Supervised learning is a foundational concept in machine learning, where a model is trained to make predictions using a labeled dataset. In this approach, we have a dataset that contains input and output pairs. The input are the data points. In the case of image classification, this is going to be an image, and the output is the corresponding label for that image. The primary goal of supervised learning is to learn a mapping from the inputs to the outputs, which will allow a model to make accurate predictions for unseen data. Training a neural network using supervised learning involves adjusting the model's parameters to minimize the difference between its predictions and the true labels. So what are the model's parameters? The model's parameters are everything from the weights and biases to the values of the convolutional filters. All of these are parameters that get adjusted during training. The training process is iterative, and it's improving the model's performance over multiple training epochs. So loss functions are crucial for training convolutional neural networks. They measure the difference between the model's predictions and the true labels. This provides us with an objective metric that the training process is trying to minimize. The loss function guides the learning process by iteratively updating the model's parameters. This enables a model to make more accurate predictions on unseen data. Choosing the right loss function is important for successfully training CNNs. For image classifications, the cross-entropy loss is the most popular loss function. The cross-entropy loss measures the difference between the predicted and actual distributions while penalizing incorrect predictions. When a model makes a prediction for a classification task, it outputs a probability distribution over the possible classes. Ideally, the predicted distribution should have a high probability for the correct class and a low probability for the other classes. For a given data point, the true distribution is typically represented as a one-hot encoded vector, where the correct class has a value of 1 and all the other classes have a value of 0. The cross-entropy loss incorporates the logarithmic function, and this has two important properties. One is that log of x approaches infinity as x approaches 0, and log of x approaches 0 as x approaches 1. In the context of cross-entropy loss, the loss will be large when the model assigns a low probability to the correct class, and small when the model assigns a high probability to the correct class. Cross-entropy loss heavily penalizes the model when it assigns a low probability to the true class. This encourages the model to be more confident in its predictions for the correct class while reducing the probabilities for the incorrect classes. In multi-class classification problems, the softmax activation function is typically applied to the output layer of the CNN, which converts the output to a probability distribution over the classes. Cross-entropy loss provides an intuitive way to measure the performance of a model in classification tasks by quantifying the dissimilarity between the predicted and true probability distributions. It encourages the model to assign higher probabilities to the correct class, and it penalizes it heavily for incorrect predictions. This ultimately guides the learning process towards a better classification performance and a better model. Backpropagation is why deep learning works. It's a critical algorithm in training convolutional neural networks. It calculates and propagates gradients through the network to update its parameters. The algorithm works by applying the chain rule of calculus, computing the gradients of the loss function with respect to each parameter in the network. These gradients are then used to adjust the parameters, minimizing the loss function and improving the model's performance. In the context of CNNs, backpropagation works differently through layers, from convolutional, pooling, and fully connected layers. Backpropagation, which only happens during training, involves several steps that helps the network make accurate predictions. First, the input data goes through each layer, where the operations, such as convolution, pooling, and nonlinear activations, are performed to generate an output. The final layer produces the network's prediction. Next, the network's prediction is compared to the desired output to calculate the loss, which measures the accuracy of the prediction. Gradients of the loss with respect to the network's parameters are then calculated to determine how sensitive the loss is to changes in each parameter. These gradients are propagated backwards through the layer using the chain rule. The network's parameters are updated iteratively using the gradients calculated in the previous step, guided by an optimization algorithm like stochastic gradient descent. These steps are repeated for each mini-batch of the training data, improving the network's ability to make accurate predictions. As fundamental as backpropagation is in the training of convolutional neural networks, it alone doesn't guarantee that the network will converge to an optimal solution. Other factors like the network's architecture, regularization techniques, and hyperparameters play a critical role. Nevertheless, backpropagation is what enables neural networks to learn and make sense of complex data. Here's how gradients are calculated and backpropagated through each type of layer. In a convolutional layer, the gradient is calculated with respect to both the input, the feature map, and the convolutional kernel, the filter. The gradients are computed using a technique similar to the convolution operation itself, but with the gradient of the loss with respect to the output from the next layer being convolved with a rotated kernel of the input. Here's how backpropagation is done through the max pooling layers. During the forward pass, the max pooling layer divides the input feature map into non-overlapping windows and takes the maximum value within each window. During the backwards pass, the gradients are propagated back, but only to the input neuron that produced the maximum value within each window during the forward pass. All other neurons within the window receive a gradient of 0 since they didn't contribute to the maximum value. This way, the gradients are routed only to the most significant activations, allowing the network to focus on important features. Like max pooling, average pooling divides the input feature map into non-overlapping windows during the forward pass, but takes the average value within each window. The gradients are evenly distributed among the input neurons, contributing to the forward pass's pooled output during the backward pass. Each contributing neuron receives an equal fraction of the gradient, allowing the information to flow back to a broader set of neurons. In both cases, pooling layers don't have learnable parameters, and their primary purpose is spatial downsampling. The gradients are primarily distributed within the previous convolutional layer, bypassing the pooling layer, ensuring effective learning and network weight updates. In fully connected layers, each neuron is connected to every neuron in the previous layer. The backpropagation process involves computing the derivative, or the gradient, of the loss function with respect to the weights and biases. Here's a bit more detail on each step. The first step is to compute the derivative of the loss function with respect to the output of the neuron. This derivative is then multiplied by the derivative of the activation function applied to the neuron's output. This gives us the local gradient, and it represents how much the output of the neuron would change for a small change in its input. Backpropagation and CNNs ensure that the model's parameters are adjusted based on the calculated gradients, guiding the learning process and enabling the network to capture complex patterns in the input data. By understanding how backpropagation works in the context of CNNs, one can gain insights into the training process and the adjustments made to the parameters at each layer in the network. Gradient descent is a widely used optimization algorithm for training neural networks, including convolutional neural networks. The algorithm works by iteratively updating the model's parameters, using the gradients calculated during backpropagation. The goal is to minimize the loss function, which will improve the model's performance. Imagine hiking in the mountains and trying to find the lowest point. You look at the landscape to figure out which direction to go in. This is similar to the concept of gradient descent in machine learning. The terrain represents a mathematical function, where each point on the terrain corresponds to a specific input. Your goal is to find the lowest point, or the bottom of the valley, representing the function's minimum value. To do this, you observe the slope or steepness of the terrain at your current location. The gradient represents the slope of the terrain. It tells you how steeply the terrain rises or falls at any given point. By moving in the opposite direction of the steepest slope, you can find the function's lowest point, or the global minimum. In machine learning, the gradient of a function represents the direction and magnitude of the steepest ascent or descent of that function at a specific input location. By moving in the opposite direction of the gradient, you can update the parameters of a model to minimize a loss function and arrive at an optimal solution. The gradient is like a navigation tool that helps you move through this mathematical landscape. By going against the steepest slope, you can find the lowest point and achieve the best solution for your machine learning task. The update rule of gradient descent is like taking small steps in the direction that leads to a better model by adjusting its parameters. It adjusts the model's parameters by subtracting a fraction of the gradient of the loss function with respect to the parameters. This helps move the model in the direction that reduces the loss, ultimately improving its performance. The formula you see here is updating your parameters. It's saying that we take the parameter and then we subtract the learning rate times the gradient. In the formula you see here, the W is representing your model's parameters. The eta, which is the N-looking symbol, is the learning rate. And the upside-down triangle, that's the symbol for gradient, is the gradient of the loss function with respect to the parameters. There are several variants of gradient descent, each with its own strengths and trade-offs, which are particularly relevant to us when we're training convolutional neural networks. The first is batch gradient descent. This method uses the entire training data set to compute the gradient and update the model's parameter in each iteration. While this approach can provide a stable and accurate estimate of the gradient, it's computationally expensive and slow, especially when you're working with large data sets and complex CNN architectures. The gradient is calculated as the average gradient of the loss function over all the training examples. Next is stochastic gradient descent. In stochastic gradient descent, the update rule is similar to the one in gradient descent, but with a slight modification to account for the stochastic nature of the algorithm. Instead of computing the gradient over the entire data set, stochastic gradient descent selects a single data point or a small batch of data points to compute the gradient. This allows for faster updates and can help avoid getting stuck in a local minima. However, frequent updates can introduce noise and make the optimization process more erratic, which can affect the convergence of your model. So here, the parameter refers to the specific weight being updated. The learning rate is the step size, and the gradient here represents the gradient of the loss function computed using a single data point. Next is mini-batch gradient descent. What distinguishes mini-batch gradient descent is using a mini-batch of data points rather than just a single data point. The gradient is computed based on this mini-batch, which allows for more efficient updates and reduces the noise compared to stochastic gradient descent. The number of samples in each batch determines the size of the mini-batch. It's usually chosen to balance computational efficiency and noise reduction. A typical mini batch size might be anywhere from tens to hundreds of data points, usually in powers of 2, and the choice that you make for mini batch size depends on the training set size and hardware capabilities. Mini batch gradient descent strikes a trade-off between the accuracy of gradient estimation, as with full batch gradient descent, and the computational efficiency, as with stochastic gradient descent. In addition to these basic gradient descent variants, there is a popular adaptive learning rate method that can further improve the optimization process called ADAM. ADAM is an optimization algorithm that combines the advantages of two other adaptive learning rate methods, ADAGRAD and RMS-prop, which we're not going to discuss here. ADAM adjusts the learning rate for each parameter based on the moving average of the gradient's first and second moments, allowing for a more efficient and stable convergence. ADAM is a widely used optimization algorithm for CNNs due to its adaptive nature and robust performance. When selecting the optimization algorithm, when you're training a network, it's usually safe to go with ADAM. You now understand how gradient descent, its variants, and adaptive learning rate methods like ADAM are crucial for effectively training convolutional neural networks. By selecting an appropriate optimization algorithm, you can ensure faster convergence and improved performance of your CNN on various tasks. Regularization and data augmentation are essential for training convolutional neural networks that achieve good generalization and don't overfit. Remember that overfitting happens when your model performs really well on your training data, but doesn't perform well on your testing data. That means that it's not generalizing to new and unseen data. There are a lot of different regularization techniques and data augmentation strategies out there that you can use to address this issue. Let's go ahead and talk about a few of them. So first, let's define what regularization even is. Regularization methods add a penalty term to the loss function, and this encourages the model to learn simpler and more general patterns in the data. Dropout is a popular regularization technique in CNNs. Now, this technique doesn't adjust the loss function at all, but what it does is it randomly drops out neurons during training. So at each training iteration, a subset of neurons is temporarily removed from the network, and their incoming and outgoing connections are ignored. This will end up building a more robust model. The remaining neurons need to learn to compensate for the missing information, and this prevents the model from relying too heavily on any single neuron. During testing, all the neurons are used, but the dropout rate scales down their outputs to account for the increased number of active neurons. L1 and L2 regularization actually add a penalty term to the loss function that's based on the magnitude of the model's parameters. So L1 regularization adds a penalty that is proportional to the absolute value of the parameters. In contrast, L2 adds a penalty that's proportional to the square of the parameters. L2 regularization is also known as weight decay, and this is commonly used for CNNs, and it leads to a smoother learned features and better generalization. Batch normalization is a technique that normalizes the input to a layer by standardizing the mean and variance of each feature across the mini batch. This helps improve training speed and stability as a form of implicit regularization. While not strictly a regularization technique, batch normalization has regularization effects because it reduces the dependency of gradients on the scale and initial values of the parameters. Now we're going to talk about data augmentation. So, although not a regularization technique per se, data augmentation helps improve your model's generalization for image classification tasks. So, data augmentation involves applying transformations to the original training examples to create new augmented examples. For CNNs, common data augmentation techniques are going to be discussed in the following slides. By artificially increasing the size and diversity of the training data set through various image transformations, the model is exposed to a wider variety of examples. This promotes the learning of more robust features. Let's go ahead and talk about some common augmentation techniques. First, let's talk about rotation. With the rotation augmentation, images are rotated by a random angle within a specified range. In translation, the images are shifted horizontally and/or vertically in a random way. With flipping, you can either flip images horizontally or vertically. So something to keep in mind when you're using the flipping augmentation or any augmentation in general is you want to choose augmentations that are going to be consistent with what you see in the real world. So let's say you have a network that is classifying cars. Well, if you're classifying cars, you don't want to flip cars upside down because in reality, out there in the real world, you typically don't see upside down cars unless, of course, they've been involved in accidents. But you want to choose flipping augmentations that are consistent with what you might observe in the real world. One of the most effective data augmentation techniques is actually the random crop, and this has been written about in papers. Random cropping is, if you were to choose one augmentation technique, I would choose random cropping. Typically, with the networks that we're going to be talking about, the input size is something like 224 by 224, right? So to do a random crop, you might have to first scale up the size of the image and then take random crops. I mean, it all depends on how big your input image is. But note that resizing an image is very computationally expensive and will take a lot of time. So it might not be the best technique if you don't have a lot of computation available to you, but it is a very, very effective technique. Next is rotation. So in rotation, the images are going to be rotated by a random angle within some specified range. Some other common transformations include color transformations that adjust the brightness, contrast, and saturation of an image. Or you can also scale images uniformly or non-uniformly within some range. So we've talked about a number of regularization and data augmentation techniques. CNNs can learn more robust and generalizable features by incorporating regularization techniques like dropout and L1 or L2 regularization, as well as data augmentation strategies in the training process. By using this technique, you're going to enable your model to perform better on unseen data. This will improve its overall performance and reduce the risk of overfitting. Understanding these techniques and their underlying mathematical foundations is crucial for effectively training CNNs. By carefully selecting and implementing regularization methods and data augmentation strategies, you can create more robust models that generalize well to new unseen data. LeNet, developed by Jan LeCun and his team in the 1990s, is a pioneering convolutional neural network that significantly impacted the field of computer vision. Its introduction marked a turning point, demonstrating the potential of neural networks in tasks such as image classification. LeNet's architecture efficiently extracted hierarchical features from input images and achieved robust performance on the MNIST dataset of handwritten digits. Its success laid the groundwork for subsequent advancements in deep learning-based computer vision techniques, inspiring the development of more sophisticated and powerful architectures. The LeNet architecture demonstrated the ability of convolutional neural networks to learn features directly from raw input data. This was a departure from the hand-engineered feature extraction methods that preceded it. This shift towards data-driven, trainable feature extraction paved the way for the emergence of modern deep learning and its widespread adoption in various computer vision applications. Compared to today's architectures, LeNet is quite simplistic, but it serves as a foundation for subsequent research in convolutional neural networks for image classification tasks. The architecture can be divided into two main parts. The first is the feature extraction part, which comprises convolutional and pooling layers. The second is the classification part, which consists of fully connected layers. Let's talk through this architecture. First is the input layer. The input layer accepts grayscale images with a size of 32 by 32 pixels. The convolutional layer is immediately after that, and this layer consists of 6 convolutional kernels of size 5 by 5 with a stride of 1. This ends up resulting in 6 feature maps of size 28 by 28. Each kernel slides across the input image, capturing local features through element-wise multiplication and summation. The original LeNet uses a hyperbolic tangent activation function for all of its layers. Next is the first pooling layer. This layer reduces the spatial dimensions of the feature maps through pooling. The 6 28 by 28 feature maps from the first convolutional layer are reduced to 14 by 14 by applying 2 by 2 average pooling with a stride of 2. This operation reduces the resolution while maintaining the key features, increasing spatial invariance and reducing computational complexity. The outputs of this layer are passed to a hyperbolic tangent activation function. The second convolutional layer comprises 16 convolutional kernels of size 5 by 5, which generates 16 feature maps of size 10 by 10. These kernels are applied to the pooled feature maps, which extract high-level features from the input image. These feature maps are then passed to a hyperbolic tangent activation function. The second pooling layer is similar to the first pooling layer. It applies a 2x2 average pooling with a stride of 2, which reduces the dimensions of the feature maps from 10x10 to 5x5. These feature maps are again passed to a hyperbolic tangent activation function. The third convolutional layer takes all 16 5x5 feature maps from the previous pooling layer and applies a 5x5 kernel with a stride of 1. Since the kernel size is equal to the input feature map size, which is 5x5, the convolution operation results in 120 output feature maps of size 1. In effect, this layer is like a fully connected layer. Each of these 1x1 feature maps is created by convolving a 5x5 kernel with a 5x5 input feature map, followed by a hyperbolic tangent activation function. The convolution layer we just discussed bridges the feature extraction portion of the network, which is all the convolutional and pooling layers, with the classification portion of the network, which will be the fully connected and output layers. By applying the convolution operation to the 16 input feature maps, this layer generates a compact representation of the input, which can then be used by subsequent layers for classification tasks. The final output layer in Linnet receives an 84-dimensional vector from the previous layer, contains neurons equal to the number of classes, and generates a probability distribution over the class labels to make the final classification decision, selecting the class with the highest probability as the prediction. So we've talked about the various layers of Linnet, and I thought it might be helpful for us to kind of get a better sense of what is happening in each one of these layers. So TensorSpace.js is a great interactive playground for you to play around with some common neural network architectures. In this case, we're going to play around with Linnet. So what we're going to start by doing is just seeing what Linnet is going to predict for a particular number that we're going to write on the pad here. So in this case, we're going to write good old lucky number 7. And for whatever reason, Linnet thinks that my 7 is a 2. But we can go ahead and kind of inspect what's happening in each layer. So we can click here and get a better sense of what's happening in each layer. So we got the first layer, the input layer, which goes into these feature maps that we can see here. Right? And as we can see, the feature maps here is what it, meaning the network, quote unquote, sees. So this is the result of the first set of convolution operations, the first set of feature maps that are learned, which go into these max pooling layers. And you can see the types of representations each layer is picking up. They begin to be more and more abstract. And then from each one of these little pixel regions, we see that the network is picking up the highest value activation. So this is a great tool for you to play around with so that you can get a better sense of what's happening in each layer. Here is the first fully connected layer in Linnet. And you can see here the brighter values represent higher activation values. And then finally, to the classification layer here. So we can reset this, and maybe if I draw a more cleaner 7 with one of those, it starts to pick that up. And there you have it. It's a great way for you to kind of get an understanding of what these abstract concepts of feature maps and fully connected layers, like what does it represent? Where is it? What's it outputting? So definitely worth checking out. AlexNet, which was developed by Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton in 2012, started the deep learning revolution. Let's take a moment to appreciate AlexNet's key contributions and impact on future architectures. First is that AlexNet introduced deeper and wider networks. AlexNet introduced an 8-layer network with a wider architecture, meaning more feature maps compared to previous architectures like Linnet. This demonstrated that deeper networks could excel in image classification tasks. AlexNet also introduces the ReLU activation function, that is the rectified linear unit activation function. This accelerated training and mitigated the vanishing gradient problem, which allowed for the training of deeper neural networks. AlexNet was also the first architecture to leverage GPU computing power to train efficiently. This paved the way for further advancements in training even larger models. AlexNet also introduced data augmentation techniques such as random cropping, horizontal flipping, and color alterations to increase the effective size of the training data set, which further improved generalization. AlexNet also introduced the use of dropout regularization. AlexNet employed dropout as a regularization technique to prevent overfitting. This enabled the model to generalize better to unseen data. It also introduced the concept of stacking convolutional layers. AlexNet demonstrated that stacking multiple convolutional layers before applying pooling could help the network learn more complex features. This is a design choice that has continued to influence future deep learning architectures. Go ahead and do a brief overview of the AlexNet architecture. It starts off with the input layer, which receives raw pixel values that are then going to be passed through the network to make a prediction. AlexNet starts off with a series of convolution and pooling layers. These early convolution layers extract low-level features like edges and lines. The max pooling layers downsample each feature map by dividing them into smaller regions and retaining only the highest activation value within each region. This helps reduce spatial dimensions of the input and captures the most important features. As we move deeper into the network, the convolution layers provide the network with a greater receptive field, which see a more holistic representation of the input. Instead of just lines and edges, it's starting to see shapes. The max pooling layers, as you're aware of now, reduce the feature map size while keeping the important features. The first set of convolution and pooling layers are followed by the stacked convolutional layers. These layers extract complex patterns and spatial hierarchies from the input data in the previous layers by building upon the representations. In a sense, this is where the networks begin to see the forest for the trees. The three fully connected layers at the end of AlexNet are responsible for taking the feature maps from the convolutional layers and transforming them into a fixed size vector. The fully connected layers enable the network to further learn complex hierarchical features. This vector is then used to output the final predictions, that is, the classification of the image. Although AlexNet has been surpassed by much more effective architectures, it still demonstrates a key step away from shallow networks to deeper networks that are used nowadays. So now I thought it'd be a good time to go back into TensorSpace.js and kind of inspect what's happening in AlexNet with each of these different feature maps, these pooling layers, fully connected layers, to kind of get a better intuition of what's happening. So on TensorSpace.js, you can select a number of different pictures. Here, let's just stick with the dog and take a look at what's happening in each one of the layers. So we can expand out the feature maps. And as you see here, the feature maps at these lower levels, they're picking up lines and edges, right? They're picking up the lines and edges. The pooling layers are reducing these larger feature maps into smaller size images, and it's starting to just keep only the values that are the brightest. So the bright that you see here, the bright pixels represent high activation values. And you can see here, as we begin to move deeper and deeper into the network, we're moving away from lines and edges, as you'll see here, and kind of picking up more abstract features almost, right? The features that we start getting into in these deeper layers are kind of beyond human recognition. We're not going to understand what it is that the network is picking up, unlike, the earlier layers where it's kind of lines and edges, but a lot more abstract representations of the image, as you can see here. And so AlexNet does this for each of its layers until it starts to move into the fully connected layers here, which we can take a look at right here. So it starts moving into the, again, max pooling and then the fully connected layers. And the fully connected layers are these really long vectors that are picking up a lot more abstract representations until it finally goes to the 1000 dimension output layer. And you can see here, it looks like this is probably the highest activation value, which is mapping to that beagle prediction. Hopefully this gives you an intuition about what's happening in neural networks. When we talk about feature maps, activation values, and, what these things represent, it's helpful for me when I started to look at this to kind of understand what it is that a network sees. While AlexNet is considered the grandfather of modern convolutional neural networks, VGG is considered the father of modern CNN architecture design. It was developed by the Visual Geometry Group at Oxford University and in 2014 took first place at the ImageNet Large-Scale Visual Recognition Challenge. VGG is known for its simplicity and depth. Before VGG, most neural networks use a variety of layer sizes and types, making them hard to scale and generalize. VGG introduced a more uniform structure using small 3x3 convolutional filters and stacking multiple layers. This approach allowed the network to learn complex features with fewer parameters, enabling it to scale to deeper architectures. The VGG architecture introduced several fundamental design principles that have impacted today's research in deep learning and computer vision. VGG showed that increasing the depth of neural networks by stacking more layers can lead to improved performance. By demonstrating that increasing the depth of the network with more layers could lead to improved performance, VGG encouraged the development of even deeper architectures with more complex building blocks. These deeper architectures often use modular building blocks to manage the increased complexity and to facilitate efficient training of deeper networks. This insight has driven the development of even deeper architectures such as ResNet and DenseNet, which employ skip connections and dense connections to effectively train very deep networks. VGG used smaller filters. It used 3x3 convolutional filters throughout the entire network. This differed from some previous architectures which used larger filters. VGG demonstrated that the small filters could effectively capture local information while reducing the number of parameters and computational complexity, a practice that has become standard in modern architectures. The use of small filters helped reduce the number of parameters and computational complexity while maintaining the network's ability to capture complex patterns. VGG also introduced the concept of stacking multiple convolutional layers with the same filter size, which could be seen as a building block for constructing deeper architectures. These blocks made it easier to design networks of varying depths by simply repeating and stacking the blocks. VGG used a consistent pattern of convolutional layers with the same filter size, 3x3, throughout the entire network, followed by its pooling layers. This homogeneous structure can be seen as a series of modular blocks, making it easy to adjust the depth and complexity of the network by simply repeating or removing these blocks. This structure allows researchers to treat the convolutional blocks as interchangeable components, making it easier to experiment with different network depths and configurations. Here's a breakdown of the VGG16 architecture layer by layer. First, we start with the input layer. Similar to other architectures, the input layer receives the raw pixel values of the input image and provides it as a starting point for subsequent layers. This is followed by the convolutional layers. VGG16 has 13 convolutional layers labeled conv1_1 to conv5_3. These use 3x3 filters to extract features from input maps. The max pooling layers are there for reducing feature map size after every 2 convolutional layers. Max pooling divides the feature maps into areas and preserves important features by keeping the highest activation value in each area. The fully connected layer, well, VGG has 3 of them, and these extract features and classify the image. The VGG16 architecture uses small filters and deep convolutional layers to capture complex visual features. The pooling layers reduce dimensionality while retaining important information, and the fully connected layers convert the high-level features into class probabilities. The introduction of this modular design is something that has stuck with deep learning researchers since the introduction of VGG in 2014. ResNet, or residual network, is a groundbreaking convolutional neural network architecture that's introduced by Kai-Ming He and his team in their 2015 paper, Deep Residual Learning for Image Recognition. In this section, we're going to explore ResNet's key features and design principles, focusing on skip connections and bottleneck layers. Skip connections, which are also known as shortcut connections or residual connections, are the backbone of ResNet's architecture. These connections bypass one or more layers in the network and allow for the output of a layer to be added directly to the output of another layer further down the architecture. The skip connection allows the gradient to bypass several layers and directly flow to the earlier layers. This preserves the gradient signal and improves training efficiency and performance. This also enables the network to learn more complex functions by allowing the input to propagate through different paths in the network. The key idea behind skip connections is to learn the residual function, which represents the difference between a layer's input and output features. Instead of learning the entire transformation, the network learns the residual, which makes it easier for the model to retain the identity function during training. This technique helps mitigate the vanishing gradient problem and allows the training of much deeper networks without sacrificing performance. In ResNet, the bottleneck layer is a specific type of layer designed to reduce the number of trainable parameters and the computational cost of training very deep neural networks, while at the same time improving their accuracy. The bottleneck layer comprises three main components: a 1x1 convolution layer, a 3x3 convolution layer, and another 1x1 convolution layer. The first and last 1x1 convolutions reduce and then restore the number of channels. In contrast, the 3x3 convolution performs the actual feature extraction. This allows for a richer set of features to be learned and enhances the layer's representational power. The purpose of bottleneck layers is to decrease the number of operations required to process high-dimensional data. This significantly reduces the computational cost associated with training the model. This design choice has enabled the creation of deeper networks with a lower risk of overfitting and reduced training time. The ResNet architecture comes in several flavors, from 18, 34, 50, 101, and even 1,000 layers. ResNet 50 is one of the most commonly used varieties of the ResNet family, and this balances depth and complexity. It has 5 stages with residual blocks using convolutions and pooling. Each stage captures increasingly complex features from the input data. Max pooling at the beginning of each stage abstracts the spatial information and increases the receptive field. The skip connections between the blocks addresses the vanishing gradient problem and allows for direct information flow. This mitigates the degradation issues associated with deep networks. This hierarchical arrangement enables ResNet to capture low and high level features efficiently. It's widely used for image classification and feature extraction due to its efficiency and accurate results. Let's briefly review the architecture of ResNet 50. The first stage of ResNet 50 is the convolution layer with max pooling. In this stage, we reduce the size of the image while preserving the crucial details in the image. We do this by employing a single convolutional layer with 64 filters. The filters are size 7x7 with a stride of 2. And this is followed by a max pooling layer, which is a pooling size of 3x3 with a stride of 2. The second, third, fourth, and fifth stages are the convolution and identity blocks. These blocks use 3 sets of convolutions with kernels of size 1x1, 3x3, 1x1. The first convolution layer in the convolution block will have a stride of 2. And then in each stage, we're progressively learning more feature maps, ranging from 128 to 512. After the series of convolution and identity blocks, the feature map goes through pooling and fully connected layers for the final output. ResNet uses skip connections to avoid the vanishing gradient problem. This makes it effective for training deep networks, 50 layers and beyond. Understanding skip connections and bottleneck layers is crucial for effectively designing and debugging deep learning architectures. These design choices allow you to create deeper and more efficient networks and provide a solid foundation for tackling various image classification tasks. ResNet's innovative design principles have had a lasting impact on deep learning and inspired the development of new architectures and techniques that build upon its success. The widespread adoption of skip connections, bottleneck layers, and other ResNet-inspired concepts continue to drive advancements in deep learning research and applications. The MobileNet family of architectures was created to tackle the challenges of implementing and running deep neural networks on mobile and embedded devices, which often have restricted computing power, memory, and energy resources. The MobileNet family has 3 distinct architectures, V1, V2, and V3. each featuring innovative designs that enhance the efficiency and accuracy of deep neural networks when deployed on mobile devices. One of the key architectural innovations of MobileNet v1 is the use of depth-wise separable convolutions. These convolutions break down the traditional convolutional layer into two distinct layers, a depth-wise convolution layer and a point-wise convolution layer that's 1 by 1 in size. This approach reduces the number of parameters required for the model, making it more computationally efficient while retaining its accuracy. In addition to replacing normal convolutions with depth-wise separable convolutions, the authors also introduced a width and resolution multiplier. The width multiplier controls the number of channels in each layer by thinning the network uniformly at each layer. Thinning means you decrease the number of channels at each layer, which leads to a reduction in the number of model parameters. Said another way, when we're decreasing the number of channels, that means we're reducing the number of feature maps. The result of this process is a model that is smaller in memory and less compute intensive, which makes it more suitable for mobile and embedded devices. Reducing the number of channels can also lead to reduced accuracy, so this approach requires careful tuning to ensure the model performs well. The resolution multiplier is applied to the input image, allowing it to be scaled down or up while retaining its main features. When the input resolution is scaled down, so are the feature maps at each subsequent layer. This makes running the neural network on smaller images possible, reducing the computational requirements and enabling further size reductions within the model. Here's a brief overview of the MobileNet v1 architecture. We've got the convolutional layers. So the input image is passed through the first standard convolution layer with 32 filters of size 3 by 3 with a stride of 2. And this layer helps to capture the basic features like edges and textures. Then we've also got the depth-wise separable convolution. These capture more complex features from the image. And this is done by applying that depth-wise spatial convolution. Remember that these are applied separately to each input channel. And this is followed by the point-wise convolution, which is the 1 by 1 convolution, which combines the output of the depth-wise convolution. So combining batch normalization and ReLU activation helps training stability and the non-linearities in the model, respectively. We also have the global average pooling. This reduces the feature map's dimensionality, which makes the network computationally efficient. This, again, is followed by the fully connected dense layers, which learns nonlinear combinations of the features from the previous layer and assists the model in classifying complex patterns. This all is followed by the softmax layer. So this outputs the probability distribution over the classes, which makes the final prediction. Taken together, the innovations of MobileNet v1 provide a powerful tool for creating architectures that perform well on mobile and embedded devices. They allow for reducing the model size and computational requirements without sacrificing accuracy, enabling deep neural networks to be deployed in a wide range of previously impossible applications on such devices. MobileNet v2's primary focus is on providing better accuracy and efficiency over MobileNet v1 while reducing computational resources and the memory footprint required to train and run a model. MobileNet v2 achieves these goals by using techniques like the inverted residual block, the linear bottleneck, and depth-wise separable convolutions. The inverted residual block is a modified residual block that consists of several layers with an expansion layer sandwiched between the two contraction layers. This improvement allows the model to reduce computational costs while maintaining better accuracy than the original residual block. Okay, so what's the difference between the residual block and the inverted residual block? As we can see here from the MobileNet v2 paper, the layers right here, the diagonally hatched layers, as mentioned here, they don't use nonlinearities. Instead, we're going to use the thickness of each box to indicate its relative number of channels. So in the classic residual, the connection is between the high number of channels. So we go from kind of a thick block or a high number of channels, contract it down to a lower number of channels, and then expand that back up. But with the inverted residual block, we're doing the opposite. We're starting with a smaller number of channels, expanding that, and then contracting that back down. Next, is the linear bottleneck. So the linear bottleneck improves the bottleneck design of other lightweight models. It replaces the traditional nonlinear activation function in the bottleneck layer with a linear activation function that reduces the number of trainable parameters by reducing the output channel size. Another innovation of MobileNet v2 is the use of the depthwise separable convolution technique. So this replaces traditional convolutions with depthwise and pointwise convolutions. So this technique enables the network to reduce the number of parameters and computations. So by combining these techniques, it allows MobileNet v2 to achieve a state-of-the-art accuracy with far fewer parameters and computational cost than other similar neural network architectures. And as we could see here from the MobileNet v2 paper, what the depthwise separable convolution looks like. So this is something we're already familiar with. If you recall, in the convolutional neural network components module, we talked about what a depthwise separable convolution does. So here's a layer-by-layer breakdown of MobileNet v2. And by now, you've noticed that there's various different ways for us to express the architecture of a neural network, whether that's an actual diagram or a drawing. More often than not, in newer network architectures, you're going to see the architecture actually expressed as a table. Makes it really easy to read. But we start with an input image. The input image for MobileNet v2 is typical of most image classification tasks, and that's 224 by 224 by 3 channels. We then move into the convolutional layer with batch norm and ReLU 6. So we have 32 filters with a 3 by 3 size and a stride of 2. Then we move into the bottleneck residual blocks. So this is the bulk of MobileNet v2. It's a number of these blocks that are subsequently learning more and more filters. So block 1, depthwise convolutional layer, and it's learning 32 3x3 filters. And it also uses the batch norm and ReLU 6. Block 2, again, is that similar depthwise convolution, and it learns more filters. And this kind of proceeds for several layers. We're learning more and more filters until finally we get to a global average pooling layer. The global average pooling layer reduces the spatial dimensions, so it averages each feature map to a single number. This goes into another 1x1 convolution layer, and this layer is connected to the global average pooling layer. And what's interesting is that this is what is going to be used for our final class predictions. So you see here, we're not using any fully connected layers. We're going from a global average pooling layer to 1x1 convolution. And then this is what gets passed to the softmax activation function, which will output the probability for each class. And this is how MobileNet is able to reduce the number of parameters by intelligently constructing these blocks and using these type of techniques to help reduce the parameter count. So MobileNet v2 is an effective and popular neural network architecture for mobile and embedded devices. By using techniques like the inverted residual block, the linear bottleneck, and depthwise separable convolutions, this architecture is able to achieve a high accuracy while maintaining a small model footprint. And this is a good choice for those mobile and embedded devices. The MobileNet v3 architecture is optimized for mobile and embedded vision applications that require low computational resources, such as smartphones and IoT devices. It was developed by Google researchers in 2019, and it's an extension of MobileNet v1 and MobileNet v2. Like its predecessors, MobileNet v3 is motivated by 2 primary objectives. 1 is maximizing accuracy, and 2 is minimizing the number of parameters and floating point operations that are used for computation. The main difference between v3 and its predecessors is the introduction of techniques like the squeeze and excitation module and the hard switch activation function. But there's an even more interesting story behind how MobileNet v3 was created, and it starts with neural architecture search. MobileNet v3 was explicitly designed using a combination of manual engineering and neural architecture search, or NAS for short. NAS is an automated approach to finding the best architecture for a given task. Instead of manually designing architectures, NAS uses algorithms to search through a space of possible designs and automatically identifies architectures that perform well for that task. You start off with a search space definition, which defines the range of all possible architectures that you can use. This includes things like the types and size of layers, the activation functions, and connectivity patterns between layers. You also need a search strategy. NAS aims to maximize a particular objective, such as accuracy on a validation data set, subject to constraints, such as computational complexity or parameter count. For MobileNet v3, the NAS algorithm was platform aware. This means it considered the requirements of mobile and embedded platforms like memory, computational resources, and energy efficiency. The NAS approach led to interesting design choices in MobileNet v3, including using the hard switch activation function and incorporating the squeeze and excitation module. MobileNet v3's NAS process considered multiple objectives, including accuracy, efficiency, and hardware compatibility. The NAS process was customized to search for architectures that would work well on mobile devices, focusing on efficiency and performance. This led to the selection of the hard switch activation function, which was found to offer a good balance between computational efficiency and expressive power. NAS also helped determine where to place the squeeze and excitation modules within the network to maximize their impact without increasing computational complexity. NAS also played a role in fine-tuning the specific configuration of layers within the MobileNet v3 architecture, such as the arrangement of bottleneck blocks and their expansion ratios. By using NAS, MobileNet v3 was able to explore different trade-offs between model efficiency, and by model efficiency, I mean computational cost and model size in terms of parameter count, and accuracy. This led to multiple configurations that were tailored for various resource constraints. The NAS process was tuned to consider the particular characteristics of mobile hardware, which led to an architecture that was well suited for deployment on devices with limited computational resources. Let's talk a bit about the squeeze and excitation module in MobileNet v3. The squeeze and excitation module aims to recalibrate channel-wise feature responses in the network adaptively. It allows the model to pay selective attention to certain channels over others, depending on what the input is like. And it works with two main steps. First is the squeeze operation. Here, global information is condensed by using global average pooling across the spatial dimensions of each channel, leading to a compact description of that channel. Second is the excitation operation. Excitation is essentially a mini network, which is usually composed of two fully connected layers with a ReLU activation in between. And this learns to scale the channels, which dynamically highlights the most important features. The squeeze and excitation module is applied after the convolution layers, but before the activation function. And by selectively emphasizing informative channels, the squeeze and excitation module improves the representational power of the network without significant computational overhead. Introducing the hard switch activation function in MobileNet v3 improved the network's performance, and it enabled it to learn more nuanced features without increasing computational cost. The hard switch activation is a piecewise linear approximation of the more computationally expensive swish activation function. Here's how it works. It takes some activation value x. Now, if that activation value x is less than -3, the hard switch activation will turn it to 0. If the activation value is greater than +3, then the hard switch value will just use the activation value. But if that activation value is between -3 and +3, then hard switch does something interesting. It takes that value x, multiplies it by x plus 3, and divides the whole thing by 6. In MobileNet v3, the hard switch function is used as an activation function in specific layers, and it replaces the traditional ReLU 6 in certain layers. Here's a summary of MobileNet v3 Large's model structure. It starts with an initial convolution layer. The first layer is a 3x3 convolution layer with 16 filters and a stride of 2. This helps the initial feature extraction and reduces the size of the image. Followed by that is a series of bottleneck residual blocks. These form the core of the architecture and consist of 3 main operations. One is the expansion layer, which utilizes a 1x1 convolution to expand the channel's dimensions, which introduces additional representational capacity. This is followed by the depthwise convolution, which operates on each input channel separately and again reduces the computational complexity. That is then followed by the projection layer, which utilizes 1x1 convolutions again to return the expanded channels to a lower dimension. This architecture also makes use of these squeeze and excitation modules, and as we discussed, these recalibrate channel-wise feature responses adaptively. You'll notice in the column called NL, this indicates which activation was used for that particular layer. Hard switch activation is used only in specific parts of the network, as is the squeeze and excitation module. The third line from the bottom, the pool 7x7 line, this is global average pooling. This is used to reduce the spatial dimensions and summarizes the feature map into a compact form, one single value. This is followed by a series of what are effectively fully connected layers. The unique components and design choices in MobileNet v3 come together to create an architecture that excels in scenarios where computational resources are constrained. The accuracy and performance achieved by MobileNet v3 is particularly impressive. MobileNet v3 achieves state-of-the-art performance in several computer vision benchmarks while maintaining the speed and efficient use of resources that have embodied the previous versions of MobileNet. For instance, MobileNet v3 is faster than MobileNet v2 while maintaining smaller parameter counts. A MobileNet v3 is built to maximize accuracy while minimizing the number of parameters and computational requirements. Using the squeeze and excitation modules, a hard switch activation function, and the use of neural architecture search make MobileNet v3 a top-of-the-line solution for image classification tasks. At the same time, its ability to adjust and customize to various use cases ensures that it is a flexible and versatile option for various applications. MobileNets have served as backbones for tasks beyond image classification, such as object detection and segmentation. They remain one of the most advanced architectures in mobile computer vision. EfficientNet is a family of scalable and efficient deep neural network architectures that achieves state-of-the-art performance on various image classification tasks. Let's talk about some key points of this architecture. EfficientNet uses compound scaling to uniformly scale all dimensions of the depth, width, and resolution. This approach helps the network find an optimal balance between these dimensions at each scale. This results in better performance and more efficiency. As the network grows, each dimension grows in proportion. This allows EfficientNet to achieve more precise accuracy with as few parameters and flops as possible. This again is what makes it an ideal architecture for resource-constrained environments like mobile devices or small data centers. EfficientNet family is actually a family of 8 architectures, ranging from EfficientNet B0, the baseline EfficientNet, to EfficientNet B7. Each subsequent model is deeper, wider, and has a higher resolution than its prior model. EfficientNet's building block is based on the MB-conv structure, which we learned about earlier in the MobileNets. It's basically just the inverted residual block. EfficientNet's MB-conv unit combines both depth-wise convolution and point-wise convolution layers with a bottleneck. These units improve the computational efficiency of the network while allowing it to extract features that are more complex. As we learned previously, the ReLU6 activation function is a variant of the standard ReLU function, and this clips the output of the ReLU activation in a range from 0 to 6. This helps prevent issues related to saturation in deeper neural networks where large activation values can cause problems during training. ReLU6 helps stabilize the learning process and improves the performance of the network, particularly in networks with a large number of layers, like EfficientNet. EfficientNet uses the squeeze and excitation optimization technique to model channel dependencies and increase the representational power of the network. The squeeze and excitation optimization method uses a set of global pooling layers to learn interdependencies between the channels in the feature maps. This allows the network to highlight relevant features while suppressing irrelevant ones by scaling the channel-wise feature maps. The squeeze step involves reducing the filters of the feature map, and the excitation step uses a nonlinear function to rescale the features. This helps the model learn more discriminative features, reduces overfitting, and improves accuracy. The EfficientNet B0 architecture consists of a stem layer followed by several blocks, each which contain multiple layers. Here's details about these layers. First is the stem layer. It has a 3x3 convolutional filter with a stride of 2, and here the network is learning 32 filters. In this stem layer is decreasing image size and enhancing depth, which is going to help the network detect those basic features. And if you remember, those basic features are lines and edges, things like that. Then we move into the MB-conv1 block. Now this is the block type from MobileNet v2, and it has 3 parts. First is expanding the number of channels using the 1x1 convolution. Then it's applying a 3x3 convolution to each of those inputs, and this is helping squeeze out more informative features using the squeeze and excitation module. And then finally, it's projecting the channels back down to a lower dimensional space using that 1x1 convolution. There are 3 blocks in a row, each with a stride of 1, which produce 16 filters. Next is followed by the MB-conv6 blocks. The MB-conv6 blocks are similar to MB-conv1, but they increase the number of channels by a factor of 6 during the expansion convolution. The model includes 13 MB-conv6 blocks altogether, with different numbers of filters ranging from 24 to 192 and varying strides, 2 for the first block in each group and then 1 for the rest. This helps reduce the spatial dimensions and increase depth. Additionally, these blocks all have the squeeze and excitation module included in them. The final convolutional layer is a 1x1 convolution with 1,280 filters. The purpose of this layer is to gather all the complex features learned by the previous layers into a large number of channels to be used for classification. Then we have the fully connected layer, and this is the final layer of the network, which is responsible for making the classification decision. It has several units equal to the number of classes in the classification problem. It usually uses a softmax activation function to output probabilities for each class. The efficient net architecture uses the swish activation function instead of the more commonly used ReLU. Swish is a smooth, non-monotonic function that works better for deeper models. The squeeze and excitation module in the MB-conv blocks has been created to enhance the network's representational power. This is achieved by adjusting channel-wise feature responses dynamically. Through this mechanism, the model can focus more or less on each channel in its feature maps, depending on how informative it deems them to be. And this is how EfficientNet B0 balances depth, which is how many layers, the width, which is how many filters per layer, and the resolution, which is the size of the input, so that it can achieve high performance on image classification tasks. EfficientNet's compound scaling, MB-conv units, squeeze and excitation optimization, and the fact that it's a family of models represents a huge leap forward in the design of convolutional neural networks. This model achieves state-of-the-art performance with far fewer parameters and far less flops in computation compared to other popular architectures. When creating a new deep learning model, it can be challenging to gather enough label data, computational resources, and time. Fortunately, transfer learning provides an efficient solution to this issue. This technique involves pre-training a model for one task and then fine-tuning it for another related task. Transfer learning is an important technique in deep learning as it saves time and computational resources that would otherwise be spent training large models from scratch. The initial layers of a pre-trained model are trained to recognize low-level features like edges and textures, which are then transferred to the new task. This is reducing the amount of training required on large amounts of labeled data. Transfer learning often leads to better generalization because the model has already learned useful feature representations from the pre-training task. Transfer learning offers several benefits for image classification tasks, which makes it a preferable approach for many practitioners in the field. Let's discuss why it's such a popular technique amongst practitioners. First is that it enables faster training and decreases the resource requirements for training a model. As I've stressed already through this video, training deep learning models from scratch is computationally expensive and takes a lot of time. With transfer learning, much of the model's knowledge comes from the pre-trained layers, which have already learned useful features in a different but related task. Fine-tuning for new tasks requires fewer resources and less time than training the model from scratch. Leveraging pre-trained models allows the new task to benefit from the knowledge gained during the pre-training process. Many pre-trained models have been trained on the ImageNet dataset, which enables them to learn a range of features. Using this knowledge, the fine-tuned model can achieve better accuracy and performance compared to a model trained from scratch on a smaller dataset. Transfer learning improves a model's generalization while requiring substantially less training data. This is really helpful in situations where you have limited labeled data. By using a pre-trained model, it's possible to reduce the need for extensive training on large amounts of labeled data. The pre-trained model already has learned features that are useful for new tasks. Since it's been exposed to a wide variety of input data, it's more likely to generalize well to new, unseen data on the target task. Transfer learning leads to faster training, improved performance, and better generalization. By leveraging pre-trained models, practitioners like yourself can tackle new problems more efficiently and with less data. Ultimately, you'll be able to achieve better results with less computation, less time, and less data. Pre-trained models play a crucial role in transfer learning as a starting point for training new models on different data sets. A pre-trained model is a neural network that's been previously trained on a large data set. For image classification tasks, that's typically the ImageNet dataset, which contains millions of images belonging to thousands of categories. Pre-trained models also help mitigate the challenges associated with limited data availability and computational power. As the pre-trained models have already learned to extract relevant features, the new model can focus on learning the dataset-specific features rather than having to start from scratch. This results in a more efficient learning process and better performance in solving the target problem. In image classification, there are two common types of transfer learning: feature extraction and fine-tuning. Feature extraction is leveraging the pre-trained model's learned features, and fine-tuning is then adjusting the pre-trained model's weights to better suit the new task. In feature extraction, you remove the last few layers of the pre-trained model and add a new classification layer. You then train the new classification layer on your new dataset while keeping the weights of the original pre-trained model frozen. So what does it mean when we say that we're freezing weights? Well, when you hear that the weights of a layer or a set of layers in a pre-trained model are frozen, it means that their weights are not going to be updated via backpropagation during training on the new dataset. This approach uses the pre-trained model as a feature extractor, which is extracting patterns and features from the input image that are then used to make the final prediction. So when we're using a model as a feature extractor and we're replacing the head of that model, the weights in the head of the model are initialized to random values. And that is what is being trained during backpropagation. Feature extraction is a good strategy to use when you have a small data set that's similar to the original data set of a pre-trained model. For example, if you want to classify images of animals, you can use a pre-trained model that was trained on a large dataset of animals, such as ImageNet, to extract features from your images before training a new classifier. On the other hand, fine-tuning involves making more extensive modifications to the pre-trained model. Instead of simply adding a new classification layer, or what's also known as a classification head, on top of the pre-trained model, you fine-tune some pre-trained layers by allowing the weights to be updated during backpropagation when training on the new dataset. You can also change the number of layers you freeze from the pre-trained model depending on the size and similarity of the new dataset. The goal of fine-tuning is to adapt the pre-trained model's learned features and patterns to the new task and to improve the model's accuracy and performance on the new dataset. Both feature extraction and fine-tuning are strategies used in transfer learning with pre-trained models. Still, they differ in terms of how much of the pre-trained model they utilize and how they adjust it to fit the new task. In feature extraction, the pre-trained models extract fixed features from the raw input data, making it easier to reuse lower-level features by training a new output layer on a new dataset. Fine-tuning a pre-trained model involves adjusting the weights to learn a new task. The learning rate controls the amount of change to the pre-trained layers. Fine-tuning does require more data and resources, but helps the model adapt better to a new task, especially if it's different from the original one. And the choice between feature extraction and fine-tuning often depends on factors like the size and similarity of the new dataset relative to the original training data and the computational resources that are available to you. Feature extraction and fine-tuning follow a similar process. I'll walk you through them now, starting with feature extraction. The first step in feature extraction is selecting a pre-trained model. You want to choose a pre-trained model that's been trained on a large and diverse data set. For example, ResNet, MobileNet, or EfficientNet that has been pre-trained on the ImageNet dataset. Second is removing the top layers for classification to modify the pre-trained model. Third is customizing the neural network for your task by replacing the removed layers with a new output layer. The output layer should match the number of classes for your use case. Fourth is freezing the pre-trained layers. You want to make the pre-trained layers non-trainable to avoid updating them on a new dataset during training. Finally, you want to train the model. Use your dataset to train the new model. Only the newly added layers' weights will be updated. The steps in fine-tuning are quite similar to the steps for feature extraction. The first step in fine-tuning is choosing a pre-trained model and replacing the output layer for your task to start the fine-tuning process. Second is freezing the pre-trained layers and training a new output layer. Now, this step is optional, but it can improve performance. The third step would be to unfreeze some or all of the pre-trained layers and update their weights. So keep earlier layers frozen for generic features and unfreeze later layers for task-specific features. Fourth step is setting the learning rate. You want to use a lower learning rate during fine-tuning to make smaller changes to the pre-trained weights, since the model is already close to a good solution. And finally, you want to train the model. New and pre-trained layers' weights are going to be updated during training with the new dataset. So if you're wondering when to use fine-tuning versus when to use feature extraction, here are some helpful hints. First is considering the size of your dataset. If you're working with a small dataset, you might want to use feature extraction because feature extraction is safer for small datasets than fine-tuning, as fine-tuning can lead to overfitting. If your dataset is large, then consider fine-tuning, as having more data helps mitigate the risk of overfitting. The next point to consider is the similarity of the new dataset to the original pre-training dataset. If the new dataset is similar to the pre-training dataset, feature extraction might suffice, as the pre-trained model has already learned useful features for your task. If the domains are different, then you might want to consider fine-tuning. This allows the model to adjust its learned features for the new task. And finally, you want to consider the computational resources you have available. Feature extraction is quicker and more efficient than fine-tuning. If you have limited resources or time, consider feature extraction, as it's quicker and more efficient than fine-tuning. Both feature extraction and fine-tuning can be powerful tools when working with pre-trained models. Understanding when to use each approach is crucial to achieving the best possible results for your use case. Let's now talk about some best practices for transfer learning. So when do you use transfer learning? Transfer learning is most effective when your dataset is smaller or less diverse than the dataset the pre-trained model was trained on, or when the features in your dataset are similar to those in the dataset used for pre-training your model. When your dataset is large and differs significantly from the pre-trained model's dataset, training a model from scratch may be more effective. How do you choose the right approach for transfer learning? Well, choosing between feature extraction and fine-tuning is based on the size of your dataset and the similarity between your target problem and the pre-trained model's original task. Feature extraction is more appropriate for smaller datasets because it reduces overfitting and improves generalization by using the pre-trained model's features as input. Now I want to talk about 4 different scenarios that you might encounter with respect to dataset size and dataset similarity, and how these situations should influence your decisions for freezing layers in transfer learning. The first situation is when your dataset is small and similar to the dataset that the model that you're working with was pre-trained on. When your images are similar, it's likely that low-level features like edges and high-level features like shapes will be similar. What do you do in this situation? You freeze the weights up to the last layer, then you replace the fully connected layer and retrain the model. Why? Because less data means you can overfit if you're training the entire network. The second scenario is if your data set is large and similar to the data set the model that you were working with was pre-trained on. What do you do in this case? You freeze the earlier layer's weights, then you retrain the later layer's weights with a new fully connected layer. The third scenario is if your data set is small and different from the data set that the model that you're working with was pre-trained on. This is the most difficult situation to deal with. The pre-trained network is already fine-tuned at each layer. You don't want any of the high-level features, but you can't afford to retrain because you run the risk of overfitting. What do you do in this situation? Well, you remove the fully connected layers and the convolutional layers that are closer to the output. Then you're going to retrain the convolutional layers that are closer to the input. The fourth scenario is if your data set is large and different from the data set the model was pre-trained on. You should instantiate the pre-trained model's weights to speed up training. Lots of the low-level convolutions will have similar weights. So what do you do in this situation? Retrain the entire network from scratch and make sure that you replace the fully connected output layer. The next consideration to make is with respect to the learning rate. During the fine-tuning process, you want to use a lower learning rate than the one used during the pre-trained model's original training. This ensures that the pre-trained weights are not drastically changed, and it preserves valuable knowledge while allowing for task-specific adjustments. Next is considerations for data augmentation. To enhance the performance of your transferred model, especially with smaller data sets, you want to apply data augmentation techniques. This involves creating new training examples by altering the original images, such as by flipping, rotating, or changing the brightness. This is going to help your model generalize better. By following these best practices, you can make informed decisions regarding the use of transfer learning and effectively improve the performance of your image classification tasks with less data and computational resources. So the few things you want to consider is to understand your dataset size and the similarity of that dataset to the dataset that the model you're working with was pre-trained on. You want to leverage feature extraction for smaller, similar data sets. You want to use fine-tuning for large data sets that are similar to the task that the original model was trained on. You want to freeze layers to prevent overfitting. You want to adjust the freezing strategy based on the dataset size and similarity. You want to use a lower learning rate and apply data augmentation to enhance the model's performance. In the examples that you'll see later, we're going to stick to the simple cases of just fine-tuning a model by replacing the model's head. In most situations that you'll deal with as a beginner, that will be enough. But I want you to be aware of the different strategies for transfer learning, because as you progress along in your journey, you need to know what to do when you encounter those situations. I'm now going to give you a crash course in PyTorch. PyTorch is currently the most popular way to train deep learning models. And in this tutorial, I'm going to introduce you to PyTorch and how to use pre-trained models for image classification. You're going to use a ResNet 50 model pre-trained on ImageNet and then fine-tune that model on the Many Places dataset. I'm going to teach you about datasets, data loaders, loss functions, optimizers, data augmentation, and the training loop. This is a bare bones introduction to using PyTorch, but it should get you familiar with the core concepts. Let's get into it. The first thing is setting up the environment. So you need to install PyTorch and Torch Vision, which are the libraries that we're going to use in this tutorial. You can simply install these using pip. But since we're using Google Colab, these are going to be already installed in the environment. And next is the Many Places dataset. So take a look at this Many Places dataset, and you'll learn that it's a image classification benchmark for the education of deep learning and computer vision. It essentially has, I believe, 100 different scene categories. These are ranging from park to airport lounge to kitchen, so on and so forth. It's a great dataset to work with, and it's the one that we'll be using throughout the remainder of this course. So the following code is going to download and extract the Many Places dataset. And the format that this directory is going to be in is what's called image folder structure. Image folder is organized in such a way that each class of image is stored in its own subfolder. This just makes it really easy to work with image classification datasets. And so this following code here, what it's going to do is going to download and extract the data set. It's going to set up paths. It's going to create a list of the classes and set up a split validation set. Then it's going to move images. So that's all this bit of code is doing here. We're going to download the Many Places data set and extract it to the datasets directory. Then we're going to set up the path to the main data set and the validation data set, and we're going to create a new directory for them. Then we're going to list all the classes in the data set by iterating over the directories in the validation data set. We're also going to create a testing data set. This will be data that is not seen at all during training, so it's going to give us a good way to evaluate the performance of our model. What we're going to do here is for each class, we're going to split the images in the validation set into a smaller validation set and a new test set using a 60-40 split. And then finally, we're going to move images for the test set from the validation directory to the test directory, maintaining the original directory structure. So all this code right here is doing is simply just setting up the data so that we can start training on it. And I'll see you in the next section where we're going to talk about the data sets and data loader classes in PyTorch. In PyTorch, datasets and data loaders are essential components for efficiently working with large-scale datasets during the training process. A dataset in PyTorch represents a collection of data. This could be in-memory data, like a list of Python objects, or out-of-memory data, like images on a disk. The dataset class provides a standardized way for you to access this data. So you typically subclass the dataset class, and you have to implement the _get_item and _length methods to return a single data item and the size of the dataset respectively. PyTorch also provides several predefined dataset classes like image folder for common use cases. The data loader is another concept in PyTorch. So while the dataset class provides you a way to access individual data items, the data loader class provides a way to iterate over datasets in batches. This is important because when training a neural network, you typically don't feed in the entire dataset at once, but you process it in smaller batches. The data loader also makes it easy to shuffle the data and use multiple sub-processes to load the data in parallel. So to create datasets and data loaders for the many places dataset, we're going to use the PyTorch image folder and data loader classes. So the image folder class allows you to load images directly from the directory structure, and the data loader class provides an efficient way to iterate over these images during training. So here's what the following code does. Right? We've got the transform class right here, right? The transforms.compose. This function is used to combine a series of image transformations that will be applied to the images. Here's a breakdown of what we're doing here. First is resize. So our input image is 224 by 224, but I'm going to resize it to 256 by 256. That way, I can take random crops of 224 by 224. Once we've done that, we need to convert this into PyTorch tensors. Next is this normalization. So the values we see here for the mean and the standard deviation, these actually represent the normalization parameters for the ImageNet dataset, which is the dataset that the pre-trained ResNet that we're working on was trained on. So normalizing data is important in deep learning because it adjusts the pixel intensity values to a standardized range. This is going to improve model performance and maximize the usefulness of pre-trained weights. This involves using the mean and standard deviation values from the ImageNet dataset to normalize pixel values in other images. This ensures they're on a similar scale and avoids suboptimal performance due to features with larger scales. So the image folder class is going to be used to create datasets for the train, validation, and test sets. The data loader is used to create data loaders for the datasets. The batch size that we're going to use is set to 64. We're going to set shuffle to true for training to ensure that the training samples are shuffled before each epoch. And we'll leave it as false for the validation and test sets. You can also inspect the classes like so. So here we're only looking at the first 10 classes. And you can see that we have 100 classes in total. In the next video, we'll talk about how to instantiate a pre-trained model. Now let's get set for training. The first thing we need to do is instantiate a pre-trained model. So pre-trained models, as we've talked about, are models that are already trained on large image datasets. Remember that using a pre-trained model is going to save time and resources, and you'll end up having better performance than training a model from scratch. We're going to access this using the torchvision.models module. And from there, we're going to import ResNet 50 as well as the ResNet 50 weights. And running this line of code, we instantiate a model. Great. Now we've got the model successfully instantiated. We have a pre-trained ResNet that we can work with. However, this model was trained on the ImageNet dataset, which has 1,000 classes. You need to modify the model to work with the many places dataset, which only has 100 classes. The part of the model that you need to modify is the last fully connected layer. This layer is responsible for producing the final output classes from the features extracted by the rest of the network. By modifying the final fully connected layer, you can fine-tune the pre-trained model to classify images into the desired number of categories. And it's as simple as this. This is how you modify the last fully connected layer to output 100 classes. Remember here that we instantiated the number of classes as so, and all we're doing is replacing the last fully connected layer. Also, need to define the loss function and optimizer. So in PyTorch, various loss functions are available for different types of tasks. For the multi-class classification task that we're working with, the best choice is to use the cross-entropy loss function. The cross-entropy loss function combines the softmax activation and the negative log likelihood loss, making it suitable for training models to predict class probabilities. So to instantiate a cross-entropy loss object, we just run the following code, like so. Optimizers play a crucial role in training neural networks. So they're responsible for updating the model's parameters based on the computer gradients during the backward pass. PyTorch gives us a number of different optimizers to use. We have stochastic gradient descent, atom, and more. We're just going to go ahead and use the atom optimizer for training. It's a safe bet. So atom, if you recall, is an adaptive learning rate optimization algorithm that computes individual adaptive learning rates for different parameters. It combines the advantages of both AdaGrad and RMS prop optimizers. To instantiate the atom optimizer, you just do it like so. We pass the model's parameter. Here we got model.parameters. So we need to make sure we let the optimizer know what parameters we're going to be optimizing. We'll specify the learning rate. So we're using a small learning rate here. And we're going to specify the weight decay, like so. Now that we've got a model instantiated, right? We've instantiated a pre-trained model. We've replaced the fully connected layer. We've defined a loss function. We defined an optimizer. Now it's time to train the model. And we'll see how to do that in the next video. All right, I can't express how excited I am for you because learning about the training loop in PyTorch is a rite of passage, and I'm so honored to be here to guide you through this rite of passage. So what is the training loop? Well, it involves several steps. It's the forward pass, the loss calculation, the backward pass, the parameter updates, and validation. So let's just quickly walk through what we're doing with these first lines here. First thing we're doing is device configuration. We're going to check and see if a GPU is available using torch.cuda is available, right? If we do have a GPU available, we're going to assign it as CUDA. If we don't, then we're going to set it to CPU, right? Then we are going to move the model to the device. We're going to move the model to the GPU. We're going to set the number of training epochs. For this example, we're just going to set the number of training epochs to 2. Note that it's going to take some time because if you recall in the previous video, we're resizing the image. When you resize an image, training just ends up taking longer because you're adding that resize operation. So if you find that this is taking longer than you would like to wait, then feel free to comment out the line of code in the transformations where we resize and just take the random crop. All right. So we're then going to initialize lists for storing the training metrics. So let's go ahead and see what happens in each loop. So inside each loop, we're going to initialize the metrics total loss, correct, and total. This is going to keep track of the loss and accuracy during training. We're then going to set the model to training mode using model.train. We're going to iterate over the training data loader, which is going to provide batches of images and labels. We're going to move those images and labels to the selected device using the .to device method. We're going to zero the gradients using optimizer.zeroGrad, and this is going to avoid accumulating gradients from previous iterations. We're then going to perform the forward pass by passing the images through the model. That's what this does here. And this is going to give us the predictions. We're then going to calculate the loss between the predicted output and the ground truth labels using the loss function, like so. And this is the forward pass, right? Just these two steps right here are the forward pass. Next, we do the backward pass. And all we do for the backward pass is loss.backward. This is going to compute the gradients of the model's parameters. We then update the model's parameters using the optimizer.step method. And that's it. That's one epoch that we've done. This right here is just going to help us keep track of some metrics, right? So during each iteration, we're going to update the training metrics. We're going to include a total loss, the number of correctly predicted samples, and the total number of samples. And then we're going to print those. We're going to average them out and print it to the console so we can monitor our progress. Output here is just going to visualize training metrics in our code. That's all it does here. Next, we're going to talk about testing and evaluation. So when you're developing deep learning, machine learning models, it's essential to assess how well they perform on real-world data. Evaluating a model helps you understand its strengths and weaknesses and provides you insights into its behavior. So here, we're going to dive into what this evaluation function is doing. So let's walk through it step by step. So the first thing here is defining a function. This function evaluate model is going to take two arguments, a model and a data loader. So the first line inside the function is going to set the model into evaluation mode. This mode is going to disable certain operations like dropout and batch normalization, and it ensures that the model will behave consistently during evaluation. Next is initializing some counters to keep track of metrics during evaluation. Total and correct will help us keep track of the accuracy. True positives, predictive positives, actual positives are going to help us compute precision and recall. And here we are going to kick off a loop. So inside the loop, we're going to iterate through the testing data using the test data loader. We're going to start by setting the torch.nograd context manager. This will temporarily disable gradient calculations. So this reduces memory usage and speeds up the evaluation process. We're going to move the images and the labels to the GPU, the same device. We're then going to use a model to make predictions. And here, we're going to find the predicted class for each image by selecting the class with the highest score from the model's output. The counters here are going to be updated. So total is going to keep track of the total number of samples, and correct is going to count the number of correct predictions by comparing the predicted class to the true labels. So that's what is going on here. These lines are going to help us calculate the true positives, predicted positive, and actual positives for the purpose of computing precision and recall. And then we are going to finally print the metrics to the console. So typically, we're going to call this function with testing data. The calculated metrics are going to be printed out, and that's going to give us insight into how well the model is performing on the test set. Remember that accuracy will give us an overall understanding of correctness. Precision is going to measure the model's ability to correctly classify positive cases, and recall is going to evaluate the model's ability to identify all the positive cases. So this code snippet right here is going to help us evaluate the model that we trained during the training loop. Now that you understand this code snippet, you're fully equipped to evaluate your model's performance effectively and get a clear picture into the performance of the model on unseen data. Next, let's talk about inference. Now, let's see how we can take our model that we've already trained and use this model to predict on unseen image data. So first thing we need to do is load an image and pre-process it for the model. And that's what we're doing here. Next, we're going to define a transformation pipeline using torchvision.transforms. This pipeline is going to resize the image to 224 by 224. It's going to convert it to a tensor, then apply mean and standard deviation normalization. So this normalization is going to take the input image and normalize it so that it's consistent with what we trained on. And in this case, this is the ImageNet mean and standard deviation. With the transformations defined, we're going to apply that to the image, which is what is going on here. Then we're going to add an extra dimension to the image using this unsqueeze zero method. This is going to make it compatible with our model because our model expects batched input. So it's just essentially going to add a batch to this tensor. Now we are going to move the pre-processed image to the GPU. After that, we're going to set the model to evaluation mode and prepare it for inference. Then within the nograd context, we're going to make predictions on the pre-processed image. So this context manager ensures that gradients are not calculated. This is going to save memory and speed up processing. Now we're going to get the predicted class and probabilities. So we extract the predicted class label by finding the class with the highest score in the model's output. To understand the model's confidence in its predictions, we're going to compute class probabilities using the softmax function, as shown here. Finally, we are going to predict the class label and its corresponding probability. And this is going to give us the insight, if you were, into the model's quote unquote perception of what is in the image. And there you have it. This block of code here shows how to use a pre-trained model to predict the class of an image. And that's it. You've got the basic workflow of PyTorch down. So for a more in-depth learning resource, I think the 0 to Mastery is a absolute must-have course. All text-based, do it all in your own time, and it goes far more in-depth than what we covered here. This is the exact same resource I used when I first started learning PyTorch, so I highly recommend checking it out to get more detailed information into how to use PyTorch. You're now about to learn about a training library called SuperGradients. So what is SuperGradients? It's an open source training library that allows you to easily train or fine-tune state-of-the-art computer vision models with one training library. So you can check it out at going to supergradients.com. You can also check it out on GitHub as well. On GitHub, you can get access to the documentation. If you ever come across any issues, you can open an issue. You can submit a question. While you're on GitHub, don't forget to give the library a star as well. That just kind of helps it get noticed by the community. And it's a good way to show your appreciation to the developers. SuperGradients also has a active Discord community, so I highly recommend joining that. If you got questions, feel free to go into there. So like I mentioned, SuperGradients is a open source training library, and it's actually built on top of PyTorch. And it gives you a easy to use framework and training library to handle pretty much every computer vision task. Right now, we will be working primarily on image classification, but SuperGradients has state-of-the-art model zoo. And in this model zoo, there are models for classification, object detection, segmentation, and pose estimation as well. So there's nearly 40 pre-trained models in the SuperGradients model zoo. And you can actually check out the model zoo by going here and scrolling down to this right here. By going to the model zoo, you can see which pre-trained models are available for you. So for example, for classification, you can see it's got a number of classification models that are pre-trained for you. Likewise, for object detection, YOLO NAS is the new state-of-the-art for object detection. So this is definitely worth checking out. And there's also segmentation as well as pose estimation. There are a number of implemented architectures in SuperGradients as well. Implemented means that the code is there for you to use, but it doesn't necessarily have the weights there for you. So pre-trained models means that the weights are there, so you've got a good starting point. Implemented means that the code is there, but you'd have to train the model from scratch on your own. So that is a high-level overview of SuperGradients. In the next video, we're going to actually see it in action and see how you can train an image classification model using SuperGradients. Now that you've got an overview of SuperGradients, let's see it in action. So this notebook that you have available to you should look a bit familiar. The first few cells in this notebook are the exact same as the PyTorch crash course. What this is doing is downloading the dataset and then splitting the dataset into the train, validation, and test sets. Once that's been done, we're instantiating our data loaders. Now, SuperGradients is a PyTorch-based training library. That means you can use your PyTorch data loaders as is without having to do anything extra. And that's a nice feature to have. So we'll instantiate our PyTorch data loaders using the image folder format. Once we've done that, we can start installing SuperGradients. So it's important to pin the version of SuperGradients so that you can reproduce the results that I have here. So if you're watching this at some point in the future, make sure that you are pinning to version 3.2.0. That way everything will run as expected. Once we've got that, it's time to instantiate the trainer and instantiate the model. So the trainer is the first thing you need to define in SuperGradients. The trainer is like the brain of our experiment. So we import it from supergradients.training, import trainer, and we define a checkpoint path. And that's this checkpoint dir. And in the trainer itself, you'll notice that we set two arguments in the trainer. These are the two most important arguments. The checkpoint root dir argument. This is the directory where results from all your experiments will be saved. After that, we go to the experiment name. So all the checkpoints, logs, and tensor boards will be saved in a directory with the name you specify here. SuperGradients supports data parallel and distributed data parallel. That's outside of the scope for this introduction to SuperGradients, but if you're fortunate enough to have multiple GPUs, I envy you. But if you had those multiple GPUs and you wanted to know how to leverage SuperGradients to use them, just go to the documentation by going to supergradients.com, clicking on Docs, again, click on SuperGradients, go to Features, Training Mode, and then scroll down to data parallel, and it'll give you an overview of data parallel. And you can see here that it's as easy as one line of code. All you'd have to do to launch data parallel is add this one line of code right before you instantiate your trainer. To launch distributed data parallel, it's exactly the same thing. You're setting up your devices and doing that right before the trainer. Now, once your trainer has been instantiated, it's time to instantiate the model. So you import from supergradients.training and you import models, and then you get the model. So here we're using a ResNet 18, but the SuperGradients model zoo, which you can go to right here on GitHub and scroll down to model zoo. The pre-trained models that are available to you are all here, and you can take whatever model you want and simply copy the string and replace this. For the purposes of this demonstration, we'll stick with ResNet 18. You also need to provide the number of classes to SuperGradients. So when you do this, SuperGradients will automatically replace the classification head to match the number of classes that you are working with. We also pass the pre-trained weights argument here with the value of ImageNet, and this will make sure that we're getting a pre-trained model. If we omit this line, then we'll end up with just the architecture without any pre-trained weights. They'll be randomly initialized weights. So this makes sure that we get the ResNet 18 architecture pre-trained on ImageNet. And in the next video, you'll learn about another important concept in SuperGradients, and that's the training parameters. All right, now that we've instantiated the trainer and we've instantiated the model, it's time to set our training parameters. There are a few mandatory arguments that you must define for your training parameters. First is the initial learning rate. So the learning rate is a hyperparameter that determines the step size at which the model's weights are updated during training. So it controls how much the model's weights should be adjusted with respect to the loss gradient. A high learning rate might cause training to converge quickly, but you might overshoot the optimal solution, or it might cause instability during training. A low learning rate might lead to more precise convergence to the optimal solution, but it could be very slow to train, and you might just get stuck in a local minimum. So picking a learning rate is important because it's balancing the speed of convergence and the stability of training. So that's an important thing to monitor. Next is epochs. This is a required hyperparameter here because an epoch is one full pass through the entire training set. So during an epoch, the model's weights are updated as it processes each batch of samples in the training data set. Once every sample has been seen and used to update the weights, one epoch is completed. So here we're using a relatively small number of epochs, just 10 epochs. So we're not going to end up with the best results for this, but I encourage you to play around with more training, more epochs, and see the results that you get. Next is defining the loss function. We're going to stick with standard cross-entropy loss function here, but SuperGradients allows you to use a custom loss function if you wish, or you can choose from one of the built-in loss functions in SuperGradients. But since we're working with image classification in this course, sticking with cross-entropy is A-OK. Next, we have the optimizer. So in SuperGradients, you can choose from Atom, Atom W, Stochastic Gradient Descent, Lion, or RMS Prop. We're going to stick with Atom here because, according to Andrei Karpathy's Recipe for Training Neural Networks, which is an excellent blog, I encourage you to check this out, Recipe for Training Neural Networks. He mentions that Atom is safe, and it's a good optimizer to use to get a baseline. He also makes a funny joke that 3e to the negative 4 is the best learning rate for Atom. So I always like to start off with his advice, even though it is a joke, to see what I get as a baseline, and from there kind of tweak my training as needed. Next, we have the validation and training metrics list. So here, we've got accuracy and top 5. So these are the metrics that are going to be displayed to us while the model is training. So accuracy answers the question, how often does this model predict the exact correct class? So it's just telling you the ratio of correct predictions to the number of items. Top 5 might be one that you're not familiar with, but it's saying that if one of the model's top 5 highest probability predictions matches the ground truth, then you count it as correct. So it's answering the question, how often is the correct class within the top 5 guesses of a model? Obviously, this makes sense in situations where you have a lot of classes. We were working with 100 classes, so using top 5 makes sense. If you're working with 5 or less classes, it's not going to make sense. So I would use your judgment for when to watch top 5 accuracy. Next is the metric to watch, which is essentially just telling the trainer the model checkpoint that you want to save. So it looks at all the accuracies from all the model checkpoints and it saves the best one according to that. In the next video, we'll talk about the optional parameters that we can use. All right, so we talked about the required parameters. Now let's talk about some of the optional parameters that we can pass to the trainer. So one of them is the optimizer params. So these are the parameters the optimizer you're using. If you leave it blank, it'll just use the default. And here's what I mean by optimizer parameters. For example, we're using Atom. So one of the parameters for Atom is the learning rate, but there's also these other parameters, the betas, the epsilons, the weight decays, so on and so forth. If you want to tweak those parameters, you would just pass them in to this as a dictionary. So I'm leaving them blank here, and it will use a default, just the pure PyTorch defaults. But it's up to you if you want to play around with that. I encourage you to play around with it and see how it impacts your training. Next is the criterion params. Now, what does this do? This is actually activating something called label smoothing cross entropy. So in the regular cross entropy laws, we're pretty strict about our label. Actually, we're very strict about our labels. The correct class will have a value of 1. All of the classes will have a value of 0. But this can sometimes lead to overfitting because a model might become too confident about its prediction and perform poorly on unseen data. So label smoothing, cross entropy, it builds on regular cross entropy by adding a touch of softness to the label. And this leads to a model that's confident, but not excessively confident. So instead of using strict 0s or 1s in the true labels, label smoothing uses something slightly softer. For example, 0.9, 0.95, 0.92, so on and so forth. This is important because it avoids overconfidence. It prevents your model from becoming too confident about its predictions. This acts as a form of regularization that can help it generalize to unseen data. It also makes the training process more stable, especially if you have noisy or incorrect labels. By softening the labels, we're encouraging the model to be a little less confident in its predictions. This ends up leading to better performance on unseen data. It's like telling the model, hey, be confident, but not too confident. Within this, you'll notice that there's this parameter called smooth eps. This is actually a hyperparameter. So it takes a value between 0 and 1 that determines the degree of smoothing that we're going to be applying to the labels. So if we have a smoothing factor of 0, that means no smoothing. And that's just giving us traditional cross entropy. But if we have a value closer to 1, that means that we're adding more and more smoothing. So it's a hyperparameter that you would typically choose based on the validation performance or through some hyperparameter tuning. Again, this is controlling how soft labels are, and it provides you a way to regulate the model's confidence or overconfidence in its predictions. The next set of optional parameters, this gets into learning rate scheduling. All right, so that's what these are controlling. So learning rate scheduling, it's an important concept. We didn't touch on it in this course, but I'll give you a quick overview of it. So learning rate scheduling involves adjusting the learning rate during training. So instead of using a constant learning rate throughout training, learning rate is being changed according to the predefined schedule or rule. So it helps find a balance between fast convergence, which uses a high learning rate, and stability, which uses a low learning rate. So there's a few different methods you can use for learning rate. It could be step, decay, exponential decay, cosine annealing. There's a lot of research that is done on this, and I encourage you to do some independent studying on this. But we also have the warm-ups, the steps, the cool down, right? So the warm-up means that, we'll start with a small learning rate and then gradually increase it until it gets to a target range. So here, what's really happening is that we're telling the trainer, start with a learning rate of 3e to the negative 4. And for the first 3 epochs, take 2 steps to get us to this learning rate of 3e to negative 1. And I'm also adding a cool down. So this is a cool down learning rate. So the cool down epochs is saying for the last epoch, taper the learning rate back down. So we kind of start with a lower learning rate, work our way back up, and then slow it back down to a lower learning rate. So why would you want to do learning rate scheduling? There's a few different scenarios that you might want to consider this. One is if you're working with large data sets. This is going to help your model converge more efficiently. 2 is if you're working with some really deep networks. So if you got a deep network with a lot of layers, controlling the learning rate is going to prevent the model from overshooting an optimal solution and hopefully get you to a global minimum. Again, it's going to help with avoiding overfitting. By gradually reducing the learning rate during the last few epochs, it might help with fine-tuning the model. It also provides greater stability during training, and it gives you a good trade-off versus exploration and exploitation. By controlling the learning rate, you balance the exploration of the lost landscape with a higher learning rate and exploitation of the promising areas in the lost landscape with a lower learning rate. So these training parameters here are what control a learning rate in the training process. So these are going to guide the learning process and help make for a more efficient and robust model. So you've learned about the required and optional training parameters that you will pass to the trainer. And you can see that this is a dictionary. It's just a regular Python dictionary that we're going to pass to the trainer when it comes training time. Note that there's a number of training tricks that SuperGradients offers right out of the box. For example, exponential moving average, zero weight decay on batch norm or bias, weight averaging, batch accumulation, and precise batch norm. You'll learn about these in a later lesson, but to use these training tricks, it's just a simple matter of adding the right flag to the training parameters. So it makes it really easy to get these really complex things that if you'd have to do it in native PyTorch, it would take additional lines of code. But with SuperGradients, it's as simple as adding one line into your training parameters. In the next lesson, you'll learn how to train the model using SuperGradients. Before we see how to train a model in SuperGradients, I just want to refresh you on the PyTorch training loop. So recall that the PyTorch training loop, you start by passing data through the model for some number of epochs. You have to put the model into training mode. Then you do a forward pass on the data. Then you calculate the loss. Then you zero out the gradients. Then perform backpropagation and then update the parameters. And as you'll see in a future video, if you want to do things like batch accumulation, it adds additional lines of code. Not to mention, with this basic bare bones training loop, we're not even printing out metrics to the log or able to monitor our training progress. It's a very bare bones PyTorch training loop, but you can see it gets cumbersome. Now let's see how we do this in SuperGradients. Once we've instantiated the trainer, all we need to do is go trainer.train, pass in the model. We have an argument here that gives the trainer a model. We give the trainer our training parameters. We pass in the training loader. We pass in the validation loader, and that's it. We are now training a model. And SuperGradients will print out a lot of wonderful information for you to the console so you can monitor progress during training. So for each epoch, we're getting a printout of the value for the label smoothing cross entropy, the accuracy, and the top 5 accuracy, as well as the validation accuracy as well. So remember that in plain PyTorch, it's not only the training loop that we have to write, we also have to write the evaluation loop. Here in SuperGradients, it's doing all of that for us under the hood. So here you can see we've trained a model for 10 epochs. I've let it train previously. Note that 10 epochs is not enough. You'll probably need to train at least 50 to 100 epochs to get decent results. But for this demonstration, it works A-okay for us. Even in this case, it took well over an hour for us to train this model. But we have it trained and we're able to see the progress during training. Once the model's been trained, well, we can get the best trained model. And it's as simple as just using models.get, and we instantiate the architecture. Once we instantiate the architecture, we instantiate the classification head, which will have a number of classes, and then we point to the checkpoint path. So in this case, the checkpoint path, if you recall, is going to be managed by the trainer. It saves it under checkpoint, under the experiment name. You'll learn about model averaging in a later lesson, but SuperGradients offers model averaging right out of the box. In this case, we'll just grab the path for the best trained model here, pass it there, hit enter, and now we have instantiated our best model. So in just a few lines of code, we were able to perform the training loop, perform the validation, and pick up our best model checkpoint. Next, we'll see how we can test or evaluate our model. Let's recap everything we've done with SuperGradient so far. We started off by installing SuperGradients, and then we instantiated the trainer. Remember, the trainer is one of the most important concepts in SuperGradient. It is the brain of your experiment, and it's what's managing all of your experiments. So we instantiate the trainer, we pass it the directory where we want to save our checkpoints, and we pass it our experiment name. From there, we instantiated our model. So for us in this notebook, we just took a pre-trained ResNet 18. We replaced the classification head to match the number of classes that we're working with. We indicated that we're using a pre-trained model, so we're getting a ResNet 18 pre-trained on the ImageNet dataset. Once we've done that, then it's time to set our training parameters. So we've got our mandatory training parameters here. We've got our optional training parameters here. And I mentioned that there are some training tricks that you get in SuperGradients for free. And in a future video, you'll see exactly how you can implement each one of these training tricks. And it's simply just a matter of adding one line to the training parameters to get each one of these. And from there, we just train the model. So remember what we're doing here, we're fine-tuning our model. So the weights are going to be updated during backpropagation. So we train our model. We grab our best trained model. SuperGradients allows you to grab 3 different checkpoints. You can grab the best trained model. You can grab the latest trained model. So if you want to pick up from training where you left off, you're able to do that. Or you can grab the average checkpoint. And we'll talk about checkpoint averaging in a future video. It's one of the training tricks that I mentioned. We evaluate our model on the test set. And this test set is data that the model has not seen at all during training with 1 line of code. And then from here, we need to get some processing parameters set. SuperGradients needs to know how to process an input image that it will be making a prediction on. So that's what we're doing here. We're grabbing the default ImageNet processing parameters, and this is going to be a dictionary. And the dictionary contains the processing steps that the image must go through, and it also contains the class names. We'll leave the processing steps alone, and we're going to replace the class names with the class names for the dataset that we're working with. We then take the best model, and we set the dataset processing parameters to be the processing parameters that we just defined. And then here, I'm defining an image URL. Really, all I did here was go to the testing set and just randomly chose an image, right? So from here, I can grab that. I can copy this path here, and I can paste it here. Now, you can grab any one of these images because these images were not seen during the training of the model. So feel free to grab any one of these images to see what the model thinks it is. Or if you wanted to, you can go online and search for your favorite aquarium or your favorite auditorium or your favorite bakery shop, what have you. Find one of these places online, grab the URL of that image and set it as this variable. And then all you got to do is then run model.predict, and it'll show you the prediction printed right atop that image. Now, if you're curious how to access more elements of the prediction, I refer you to the SuperGradients documentation. So you go to the SuperGradients GitHub. While you're here, be sure to give the repository a star. Go to documentation, go to source, and you'll see here that there's a number of documentation for you to look at for the various aspects of SuperGradients. You want to scroll down here, go to model predictions. Everything you need to know about accessing the model's predictions will be made available for you here. And that's it. In the next video, you are going to be introduced to a template. And my claim is that this template will get you through 90% of image classification problems. And I look forward to seeing you in the next video. All right, so now that you're familiar with SuperGradients, I'm going to show you how you can solve 90% of all image classification problems using SuperGradients. This is a templated notebook I've created for you that's going to make it really easy for you to get up and running with any image dataset, as long as it's in image folder format. Now, luckily, most image classification datasets are in image folder format, so you'll be in luck. So the first thing we do, obviously, is install SuperGradients and import some required modules. One thing I want to talk about that's different from the previous video is now we're going to use a configuration file. So configuration files are useful in deep learning because they provide a convenient way for you to store and manage various settings and parameters for a training process. So some reasons why a configuration file is beneficial is that one is modularity and reproducibility. If we're able to separate the configuration from the code, you can easily modify or experiment with different settings without changing the code itself. So this modularity promotes reproducibility because you can precisely record the exact setup that was used for the different experiments. Configuration files allow you to specify various hyperparameters, model architectures, optimizer choices, etc. So having a configuration file makes things very flexible for you. It also gives a more simplified experiment management workflow. With the configuration file, you could store all the required settings in one place. So this simplifies your experiment management. So what we have here is we're just going to define the root directory that you're working in. We're going to point to your test, train, and validation data sets. You can have your checkpoints directory. You can name this whatever you want. You can name your experiment whatever you like as well. This is going to be useful for when we instantiate the model. We'll just leave the pre-trained weights to ImageNet. As you recall, with SuperGradients, once the model is trained and we're looking to get the best model, we can choose from either the best, latest, or average model checkpoint. Well, I'm just putting the best one here, but you can change it to be average or latest if you'd like. This is for image preprocessing, so we'll just leave that information here. Likewise here, for image preprocessing, you can choose your own batch size. It should be an integer that you choose for your batch size. Depending on the size of your images and the size of your GPU, you might need to choose a smaller batch size. I think starting with 32 is a good rule of thumb. And then from there, you can move up by powers of 2. So for example, 32 to 64 to 128, or scale down from 32 to 16 to 8 or 4. This is just for the device management. Here is for the training parameters, which we'll see later. We're also defining the loss that we're using, the optimizer, the number of epochs, and the initial learning rate. You'll also have to set the number of classes for your new data set, and also the metrics that you are watching during training. This code should look familiar. This is just instantiating the Torch data loaders. So here we're using image folder format. And now here's the training parameters. So if you recall in the previous videos, we built the training parameters from scratch. Now the training parameters actually are a form of a recipe. In deep learning, a training recipe refers to a set of steps or guidelines that outline the process of training for a specific model. These training recipes are useful because it makes it easier to transfer knowledge and techniques from one project to another. It also enables documentation and reproducibility, right? Training recipes will serve as documentation. It documents all the steps and decisions that you made during the training process. This again facilitates reproducibility because others can follow this recipe and get the same results that you obtained. It also helps with experimentation and iteration because it gives you a structured framework to experiment with the various hyperparameters, training strategies, and architectures. And it also helps foster community and collaboration because training recipes can be shared with the deep learning community. And this will allow you to reproduce other people's work. Other people can reproduce your work. You guys can build upon each other's work. So the beautiful thing about being in deep learning is the culture of open science and transparency. Now from here, we're getting the default training params, which we defined in the configuration file above. We're also going to have to set some configurations on our own. So this is the default training params. It kind of brings in a bit of everything, but we have to set some of the parameters ourselves. For example, the loss, optimizer, number of epochs, the metrics that we want to watch, and the initial learning rate. And we do that, and we can see that we've got all that updated here for us. You'll also learn in a future video how you can implement and use some of the training tricks. And it's going to be as simple as just adding a line of code like this to your training parameters. But you'll see that in a later video. Now we instantiate the model, just like we did previously. We instantiate the trainer. These two can be done in any order. In the previous video, I instantiated the trainer, then I instantiated the model. It doesn't matter what order you do that. And then we train the model, just like we're familiar with doing. We load the best model from the checkpoint that we want to load from. We evaluate the model on the test set. And then finally, we can predict on some unseen data. And your homework that I'd like you to do is play around with some of the different models that we have available in the SuperGradients Model Zoo. So I've made it easy for you to go ahead and get started. You can choose from these different models and the different training parameters. And these will serve as a guideline for you to select a different model. From here, you're ready to take on almost any image classification challenge. Hopefully you do this on Kaggle. If you come by to the Deep Learning Daily community, I'd be happy to help you there. But the world is yours now. Have fun, go out there and train models and enjoy this newfound power that you have as an image classification wizard. Getting trapped in a false local minima sucks. When you're training a neural network, chances are you're using mini batches. There's nothing wrong with that. It just happens to introduce noise and less accurate gradients when gradient descent updates your model parameters between batches. Exponential moving average is used in training deep neural networks to improve their stability and generalization. Exponential moving average, or EMA for short, is often applied to model weights. Instead of just using the raw weights that are directly learned during training, EMA maintains a running average of the model weights, which are then updated at each training step. It combines the previous average and the current model weights, each of which are scaled by some value alpha. And here's the formula for exponential moving average. The P here represents the model parameters. So P1 is the parameter at time step 1. PT is the parameter at some time step t in the future. EMA Sub t is the exponential moving average at time step t, and correspondingly EMA t minus 1 is at the previous time step. Alpha is a smoothing factor that's usually between 0 and 1. So let's think about what this formula is telling us. It's giving more importance to recent values. It combines a portion of the current value with the previous average, thus creating a smoothed, continuous line that follows trends, but reduces sudden jumps and fluctuations. Let's talk a bit about the alpha parameter in EMA. The alpha parameter is a number between 0 and 1 that affects how much importance is given to recent data when calculating the exponential moving average. A higher alpha means recent data is weighted more heavily, and that exponential moving average is going to be more responsive to recent changes. A lower alpha means older data is given more weight, and the exponential moving average will be slower to respond. Adjusting the alpha balances responsiveness and noise reduction, but takes some trial and error to find the best value for a specific problem. When training a neural network, small batches of data, known as mini batches, are randomly selected from the training data for training. This technique adds noise to the training process. This noise is sometimes good. It can enhance optimization and result in better local optimas being reached. However, the noise can also cause optimized parameters to fluctuate around a local minimum when the parameter optimization is almost complete. EMA reduces this noise and makes the parameters more likely to be closer to a local minimum. It helps stabilize the training process by minimizing noise in the parameter updates, which leads to more stable convergence and better model generalization. EMA smooths out fluctuations and noise in the training process by averaging the weights over time. This could lead to a more stable and robust model. The smooth weights often generalize better to unseen data. While the raw weights might overfit to the training data, the EMA weights tend to capture broader trends, improving validation and test accuracy. EMA can lead to faster convergence, as the smoothing helps the model navigate the loss landscapes more efficiently. EMA can be applied to various neural network architectures and is often used with optimization algorithms like ADAM. EMA is an excellent training trick to use if you're noticing that during training, your model's loss is fluctuating wildly. It'll help smooth out the loss and lead to a more stable training process and model that is able to generalize better. Everyone loves a free boost in model accuracy, and that's precisely what weight averaging offers. It's a post-training technique that combines the best model weights from multiple training epochs and averages them into a single model. The idea behind weight averaging is to create a more robust model that's less sensitive to the specific weights learned at the final training step. By averaging the weights from different stages of training, the model can generalize better to unseen data. This effectively creates an ensemble of N models, where N represents the number of best checkpoints used. Although not identical to averaging the predictions of N models, this method provides similar benefits without the added cost of running inference on multiple models. Weight averaging helps overcome the optimization algorithm's tendency to get trapped in the local minima or oscillate between adjacent local minima during the later stages of training. Mitigating these effects not only enhances performance, but also reduces bias. This technique does not directly impact the training process. It simply requires storing additional weights on disk throughout training. Weight averaging has proven effective in various scenarios, particularly when training deep neural networks with complex loss landscapes. It can provide a notable boost in performance when models are prone to getting stuck in local minima or oscillating between adjacent minima during the later stages of training. When the training process involves lots of fluctuation, weight averaging stabilizes the model's performance by using weights from multiple stages of training. When dealing with complex models that are prone to getting stuck in local minima, weight averaging can help with optimization issues in these complex models by offering a more resilient group of parameters that represent an average across the training phases. When the model is prone to overfitting, weight averaging can improve its ability to make accurate predictions by smoothing out parameters, thus preventing overfitting. Weight averaging involves storing model weights from different training stages without extra training or computational resources, which makes it valuable in situations where you have limited resources. Here are some situations where you don't want to use weight averaging. One is if your model is underfitting. If your model doesn't fit well, it may need more complexity to capture patterns accurately. Weight averaging may not help much, and you may need to increase the model's complexity. When the model's performance doesn't vary much during training, then weight averaging may not improve the performance if the model remains stable during training. If your computational resources are extremely limited, then weight averaging might not be a good idea. Although it doesn't require extra training, it does require storing model weights from different stages of training. And this could be an issue if you have limited computational resources, specifically with respect to memory. When the model's weights are not independently meaningful, then the weights might have specific constraints or interdependencies that make weight averaging inappropriate. Weight averaging may not be appropriate for models with intricate interconnections between parameters or where weights are initialized with specific significance. Weight averaging might be less effective for shallow models with simpler loss landscapes or when the optimal weights are significantly different across training epochs. Weight averaging is a powerful technique for deep neural networks. It stabilizes performance, prevents overfitting, and improves accuracy on unseen data. However, factors like underfitting, limited resources, especially with respect to memory, and non-meaningful weights must be considered. When used correctly, weight averaging enhances model performance and generalization, making it an invaluable tool for deep learning. Have you ever tried to adjust a recipe to fit the ingredients, cookware, and oven that you have on hand? It's not an easy task. And the same can be said for using off-the-shelf models with a suggested training recipe, which usually recommends a powerful GPU for training. Not everyone can access high-end GPUs, and premium cloud-based options can be expensive. What if you wanted to reduce the batch size to accommodate your hardware? You would need to tune other parameters, which would potentially affect your training results. But there's a solution to train models that are going to be appropriate for the constraints of your target hardware. And this is called gradient accumulation, which is also known as batch accumulation. And you'll hear me use these two terms interchangeably. The process of gradient accumulation or batch accumulation involves splitting the batch of samples into several smaller mini batches. These mini batches are typically quite smaller, as small as 4 or 8 samples. The gradient accumulation reduces RAM usage significantly and lets you imitate training on larger batch sizes that normally your RAM wouldn't allow you to do. This allows you to simulate a larger batch size. During each forward pass, the network generates predictions for the samples and calculates the loss value at each sample. It then computes the gradients of those loss values with respect to the model parameters. Now, instead of immediately updating the model parameters, these gradients are accumulated over multiple forward passes. Here's what it looks like in code. On the left-hand side is the standard PyTorch training loop that you had learned about earlier. On the right-hand side is a modified training loop that uses batch accumulation. So inside each epoch, the training data is divided into batches, which are going to be processed by the model and have a loss calculated. The gradients are then accumulated over a specific number of steps, and this is what the variable here, accumulation steps, holds. And the model's weights are going to be updated accordingly. After updating the weights, the gradients are going to be reset to 0, and then the process, including gradient accumulation, will help in optimizing the model's performance by iteratively refining its parameters. Suppose you have a batch size of 32, but you want to effectively use a batch size of 128. Well, instead of updating the weights after every batch of 32 samples, you can accumulate the gradients of 4 batches of 32 samples before updating the weight. This way, the effective batch size is 128, but the memory requirements are still the same as a batch size of 32. And this is a key advantage of batch accumulation. It allows for the effective use of larger batch sizes without exceeding the GPU memory constraints. The end result is more stable training and more smoother training, which could lead to better model performance. Since gradients are accumulated over multiple mini batches before a single update is performed, the training process may require more time, especially if the accumulation step spans many mini batches. Small batches are noisy and can lead to instability, but have a regularizing effect and may lead to more global optimums. Larger batches are more stable, but sometimes they might generalize worse. Despite this trade-off, gradient accumulation remains a valuable technique for adapting the training process to different hardware configurations while preserving model quality. To sum it all up, gradient accumulation adds up gradients from small batches to allow a virtual larger batch size, which in turn will enable large-scale model training without requiring more GPU memory. So this is a perfect solution when you are in a situation with limited GPU memory constraints. It might slow down training, but generally it will improve model quality and facilitate smoother, more stable training, leading to better performance. It's a valuable technique for adapting training to various hardwares while maintaining model quality. Precise batch normalization is a technique used to improve the accuracy and consistency of batch normalization statistics during the training of deep learning models. Let's begin with a brief overview of what batch normalization is. Batch normalization is a technique used during the training of neural networks to normalize the output of a previous layer by subtracting the batch mean and dividing by the batch standard deviation. This normalization helps stabilize the learning process and reduce the number of training epochs required for training deep networks. Batch norm, as it's also known, is a method that normalizes the activations of the neuron in a layer on a per mini-batch basis. So it takes a batch of inputs and adjusts them during training so they have a mean of 0 and a standard deviation of 1. This keeps the values flowing through the network in a more controlled range. Here's how it works. First is normalization. You adjust the activations in the batch to have a mean of 0 and a standard deviation of 1. This is followed by the scale and shift, applying scaling and shifting with parameters learned during training to fit the data's original distribution if needed. Batch normalization does have its flaws. For example, batch norm normalizes features based on the batch mean and variance. Small batch sizes can lead to inaccurate estimates and unstable training, a common issue due to memory constraints. Batch norm uses batch statistics during training and running averages during inference, which can cause discrepancies, especially with small batch sizes. Poor initialization of network parameters can affect batch norm's performance, leading to unstable training with exploding or vanishing gradients. Batch norm can make it difficult to train very deep networks because the normalization process can wash out useful information in the deeper layers of the network. Here's how precise batch norm addresses these challenges. Precise batch norm uses larger batch sizes during training to improve the accuracy of computed statistics. This is achieved by accumulating statistics across multiple mini-batches. Precise batch norm uses the same statistics during training and inference, which improves the model's performance. Precise batch norm uses a synchronization mechanism to ensure that the statistics are consistent across different devices. And this approach ensures that all devices use the same statistics, which can lead to more stable and consistent training results. Precise batch norm uses stratified sampling to ensure accurate estimated statistics, even when the data is not identically distributed. Precise batch norm addresses the challenges associated with traditional batch norm by combining larger batch sizes, consistent statistics across training and inference, synchronization across devices, and stratified sampling. These strategies help improve the estimated statistics accuracy, leading to more stable training and improved model performance. Weight decay is a regularization technique commonly used in training neural networks, where a penalty on the weight is added to the loss function to prevent them from growing too large. Most computer vision tasks involve models with batch norm layers and biases added to linear or convolutional layers. More parameters in the model can help capture interactions between different parts of the network, but they also increase the risk of overfitting. That is where regularization techniques like weight decay come into play. Weight decay essentially pulls weights towards 0. While this is beneficial for convolutional and linear layer weights, it's not ideal for batch norm layers. Batch norm layer parameters are meant to scale and shift the normalized input of the layer. Forcing these values to a lower value would adversely affect their distribution and result in an inferior model. Batch norm itself has a slight regularizing effect. Adding weight decay to the batch norm parameters might introduce unnecessary or conflicting regularization, which doesn't align with the intended behavior of the batch norm layers. In scenarios where training is done with small batch sizes, applying weight decay to the batch norm parameters may amplify the noise in the estimation of the mean and variance. Weight decay effectively pulls these parameters towards zero. Again, this is not optimal behavior for those parameters. Since batch norm parameters are involved in scaling and shifting the activations, applying weight decay to them is going to inadvertently constrain the expressive power of the network. It's best to avoid weight decay for batch norm and bias parameters in deep learning because this will negatively affect the model's performance. These parameters are designed to adjust and scale the input of the layer, so forcing them towards zero can lead to subpar results. Balancing regularization and preserving the benefits of batch norm layers requires careful control of weight decay for these parameters. While the application of weight decay to batch norm parameters and biases is somewhat dependent on the specific task and architecture, there's a growing consensus that excluding these parameters from weight decay might often lead to better training stability and generalization performance. It's an example of a subtle implementation detail that can have a significant impact on the resulting model. Training a model to perform at its best can be a challenging task. You've explored the intricacies of various training techniques, from precise batch norm, weight averaging, and batch accumulation. You've learned how these can improve a model's performance and stability. Now it's time to take the next step and see these concepts in action. In the SuperGradients framework, implementing these training tricks is straightforward and efficient. Let's dive into the code and demonstrate just how easy it is to take advantage of these powerful techniques with your own models. So, you've seen in previous videos the workflow for training with SuperGradients. To implement these training techniques, all you have to do is toggle some parameters in your training parameters. So what we're going to do here is download the default training parameters, and you can take a look at the values for the default training parameters. We'll leave these default values as is now, and I'm going to show you how easy it is to implement each one of these, starting with exponential moving average. So let's recap what exponential moving average does, right? Getting trapped in a false local minima sucks. So when you're training a neural network, chances are you're using mini batches. There's nothing wrong with mini batches. It just happens to introduce noise and less accurate gradients when gradient descent updates models' parameters between the batches. On one hand, that's nice because noisy gradients can sometimes help optimization and lead to a better local optimum than if you trained on the entire data set. On the other hand, the noisiness might lead to converging to a false local minima. Luckily, you have the exponential moving average at your disposal, and we've learned about this method before. It makes your models more stable, improves convergence, and helps your network find a better solution. And it is as simple as just toggling a parameter in SuperGradients. So you can see here that the default value for EMA in the training parameters is false. If you want to turn it on, this is all you got to do. There you go. There's also parameters that are associated with exponential moving average that you can tweak and toggle. My recommendation to you is to leave these as default values and play with them if you want to just kind of see the impact toggling these parameters has on your training. I'll leave that exercise up to you. Next up is weight averaging. Everybody likes a free boost in model accuracy, and that's exactly what weight averaging gives you. It's a post-training method that takes the best model weights across training epochs and averages them into a single model. By averaging weights for the n best checkpoints, you're effectively making an ensemble of n models. It's not exactly the same as having n models and averaging their predictions, which comes at the price of running inference against n models, but it can help with squeezing out some extra accuracy. And it does this by overcoming the optimization tendency to alternate between adjacent local minima and the later stages of training. It also has the added effect of reducing bias. Let's start from scratch here. So I'm going to re-download a fresh set of default training parameters. And you can actually see here that the default value in SuperGradients is to set that equal to true. If you're in a situation where you don't have enough disk space to save all these weights to disk, you can just toggle it to be off just like that. And you're done. Now let's talk about batch accumulation. As we talked about previously, most off-the-shelf models come with a suggested training recipe, which usually suggests a powerful GPU for training. You might not have a powerful GPU at your disposal, and you might want to tailor your batch size so that it could work on your target hardware. So this is how it works. Batch accumulation starts by performing consecutive forward steps over your training data set. Then you accumulate the gradients, and then you back propagate them every few batches. You want to be sure that you're training with a batch size that's small to begin with. Typically 4 or 8 should be good for most smaller GPUs. Next, you want to determine the virtual batch size that you want to simulate. So let's say you can only fit a batch of 4 onto your GPU, but you want to simulate a batch size of 64. then you would want to accumulate for 64 divided by 4, which is equal to 16 batches. And let's see how you do this with SuperGradients. So downloading the fresh set of parameters there. And just to show you what the default value is going to be in SuperGradients for this, the default value is going to be 1, right? But you can change that. And in this case, we'll change it to be 16. So now if you're training on a batch size of 4, but you're accumulating for 16 batches, that means that you have a virtual batch size of 64. Now let's talk about precise batch norm. So batch norm itself is a wonderful invention. Ever since it came out in 2015, it's been making models less sensitive to learning rates and choice of initialization. But it does have its problem. As a matter of fact, Jan LeCun, the head of artificial intelligence at Meta AI, once said that batch normalization in the mind of many people, including me, is a necessary evil, in the sense that nobody likes it, but it kind of works. So everybody uses it, but everybody is just trying to replace it with something else because everybody hates it. So batch norm gets a lot of flack, and we learned about why in the lecture. So we're going to use precise batch norm here. So again, this is completely optional for you. We'll start by getting a fresh set of training parameters, and then you can see here that the default value for precise batch norm in the training parameters is going to be false. And we can go ahead and set it to true. Now, if you want to use precise batch norm, it's preferable to set the batch size to something small when you're training. You want to, again, mimic a scenario where you can't fit a large batch on your GPU. Then you want to set this value, precise batch norm size, to be large enough until you see some good results. So again, this is a hyperparameter that is up to you to play around with. I put 256 here, but you can choose values as large as you'd like and just assess what that does to your training. Now let's talk about zero weight decay on batch norm and bias. So as you know, most computer vision tasks have batch norm layers and biases along with linear and convolutional layers. This tends to work well because you'll have more parameters in your model. But more parameter means more ways to capture intricacies between parts of your network. But more parameters also means the opportunity to overfit a model. And we talked about at great length in the video for zero weight decay on batch norm and bias, the problems that presents. And to go ahead and implement zero weight decay on batch norm and bias, all you have to do is set the training parameter to be true for that. And that's it. You don't have to write your own custom code to implement a lot of these training tricks. It's just a matter of setting the appropriate flag in SuperGradients in the training parameters. And as you know, as you've seen in the SuperGradients lessons, that this training parameter dictionary gets passed to your trainer and it'll implement everything for you right under the hood. There you have it. Now you know how to implement these training tricks in SuperGradients. That brings us to the end of the course. And now you finally know what the words on this shirt mean. But this isn't the end of your deep learning journey. It's only the beginning. I encourage you to learn more by exploring what SuperGradients has to offer. A next step from here is learning to use SuperGradients for tasks beyond image classification, such as object detection, semantic segmentation, and pose estimation. Be sure to check out YOLO-NAS, a state-of-the-art object detection model available in SuperGradients. Learning is always better when you're with a community, so consider joining the Deep Learning Daily community to hang out with deep learning practitioners like yourself. Again, my name is Harpreet Sahota. Connect with me on LinkedIn, X, and Threads under the handle Data Science Harp. And thanks for taking time out of your schedule to complete this course.